So well, I'm checking here the participants that are online. So let's check to confirm with the program that I have. And we check who's present. Okay, timetable. Okay. Okay, so you see, this is the timetable.
Yes.
I have. So let's see who's here. So first we will have the greetings from Professor Jiangong, then Professor Joseph Subuti, then Daniele Gregoris, Wenbin Lin, Soroush, Shakeri, and Wenbin Lin. So I saw Daniele, I saw Wenbin Lin, but I don't see anybody else from this list. What about Professor Jiangong Gao? There are some greetings that will be read for by someone, or do you know something about Young?
No, I don't have any information about him.
Okay. Well, I think that anyway we can go ahead then. If there is Yang Gongao, Professor Yang Gongao is not here, and I don't see Professor Yusef Subuti either. So what was your question, Professor Kadir, that you would like to leave a message, Professor Ruffini? Did I understand correctly?
This is Jiangong Gao.
Oh, great, Professor. Good morning, welcome.
Where is the Remo? I can't see him.
No, I don't see him at this moment. You know, Professor, that Professor Ruffini is in the hospital. He's in the hospital.
Oh, I'm sorry.
So he is getting connected. Yesterday he was online with us the entire day, but you know how it is in the hospital. Maybe sometimes there is someone. We are waiting for him today. Actually, he will be leaving today from the hospital. So we are during this today. He, at any time he could just get out from the hospital and come here, just stay with us in person in Nice. So, but unfortunately at this moment I don't see here online. But you know, we are recording everything this session, so he for sure will be
Hello.
Here he is, Professor Ruffini.
Okay.
Good morning.
Okay.
Hello, Remo.
Good to see you.
This is Gao.
Yes, what a great possibility that we have to speak to each other.
Yes.
I am really thankful that you did this special effort. And I like very much all the beautiful words you say about Tulufan and the mountain and the lake. And it's my dream continuously. Where are you these days? Which part? In south of China?
Now I'm in my hometown, Lintao, Gansu province, the center of China, not Urumqi.
Yes. Good. How is your family? Everything okay?
Very well. Good.
Good.
Benissimo.
Benissimo.
Thank you. Thank you.
Good.
So the time is flies.
Yes, but we are still participating, and that is the important point.
Yes.
And we are discovering.
I remember the 40 years ago. I still remember the party for your 40th birthday in China.
Yes.
Now it's the 80th birthday. Life has gone so fast. 40 years ago, after the Marshall Glassman meeting in Shanghai, you visited the Urumqi, Xinjiang, the center area of the Asia, and the northwest border of China. You left footprints in the Trufan, the heavy pour, the lake on the top of the Tian Shan Mountain, and the Tian Shan Glacier. You have greatly contributed to the widespread of the new knowledge and the progress in modern astrophysics. You helped to build a connection among university, college in Xinjiang and the ICTP. And significantly promote the academic communication between scientists in this relatively closed region and the outside the world. You sowed the seeds of science and the friendship in this region. These seeds have sprouted and are growing. Now, astrophysics research group has been established in the Xinjiang University. The former Xinjiang Institute of Technology has been merged into the Xinjiang University. And the courses of general relativity and the relativistic astrophysics are offered to the graduate students. Your efforts for scientific and cultural exchange between China and Italy will never be forgotten. Auguro un buon compleanno.
Grazie, grazie, grazie. Grazie molte.
Allow me to conclude by congratulating your birthday in Chinese. 祝你生日快乐，寿比南山。
Thank you so much, Gao. Thank you so much.
Thank you.
So that's all. Grazie.
Thank you very much. It is really a pleasure to see you and to receive these beautiful words and this remembrance. They have been a high point of my life, and I still remember our colleagues of the university, the rector who came to Rome, and say hello to them. And then, of course, there is even a student, former student of mine, who is now in Urumqi. And I still, at the astronomy department, I still hope to visit them. Okay, and thank you again.
Okay.
And we have contact also on the other side of Tian Shan with the people in Alma-Ata. And that part also is very beautiful. It's still Tian Shan. And it's a beautiful name, Tian Shan.
Chen Shan.
properly chosen for such a beautiful place.
Welcome you visit there again.
Thank you again. Thank you. Yes, I will.
Thank you, Professor Gao. So we have to continue. Second words today. Professor Joseph Subuti is a Professor Subuti online. I don't see him in the list of participants here online. But I see Soroush. Soroush, you know something about Professor Subuti? He's a...
Can you hear me, Jorge?
Yes, we can hear you, Soroush.
Hello to all. I don't know because also I called him, but he did not respond. I don't know. I'm trying to call him on phone and let you know in few seconds.
Oh, okay, Soroush. In the meantime, we just go ahead with the program, and then if he comes, then we give him the floor. Okay. So let's continue with Daniele then. Daniele Gregoris.
Good morning, everybody. Can you hear and can you see me?
Yes.
Very well. We can see you very well.
Perfect. So I try to share my screen.
Go ahead, please.
Okay. Okay. So good morning, everybody. My name is Daniele Gregoris, and I come from Jiangsu University of Science and Technology. In my talk, in the first part, I will share some personal memories, and instead I will spend some words about my current research interest in its second part. So, okay, how to move? Okay, so I met Professor Ruffini for the first time in 2010 spring semester, when I attended his course on gravitational physics, black holes and cosmology at La Sapienza University. In September that same year, I joined his group 9 at La Sapienza University in relativistic astrophysics for writing my master thesis. Here you see its cover with the name of a candidate and the name of a supervisor inside this red circle. And although I was a very young student without experience, Professor Ruffini offered me some very interesting opportunities. For example, as I said, I joined his group in September, and in December that same year, after a couple of months, I was invited to attend the IGRANET annual meeting in Pescara. So you can see the group photo, and you can see that, for example, also Nobel laureate Riccardo Giacconi attended there. Then I defended my thesis at the university, and a very few weeks after, I was given the opportunity of presenting my research interest, my research result at my first international conference, which was the 12th Italian Corren Symposium on Relativistic Astrophysics, also held in Pescara. Then I continued as a PhD student in the Erasmus Mundus program. Here there is a photo taken 10 years ago in front of Villa Ratti, if I remember correctly, when we were attending our School of Physics at Nice University. And you can see that there are participants, colleagues from all over the world. And so I believe that this took a lot of organizational effort, for which I should be thankful to Professor Ruffini. I would like to single out one specific experience among many, which is when I attended the Galileo Xu meeting in Beijing in 2015. In fact, as I said, my current affiliation is Jiangsu University of Science and Technology, which is located in Zhejiang. And indeed, in what follows, I will present some fruitful research outcome with a colleague located in that same province. And I believe that this opportunity of attending the Galileo Xu meeting gave me the opportunity of discovering that part of the world and that part of the international scientific community that I would have not discovered otherwise. So let's now move to a more technical part. We are all familiar with the concept of reversible versus irreversible transformations of black hole and the related notion of black hole irreducible mass formulated by Christodoulou and Ruffini in their 1971 paper. Very recently, I came across a republication as a golden oldie paper by Brandon Carter, so by a third independent author. And in this paper, I found written black on white that irreducible black hole mass is essentially the area of the surface of the black hole horizon. In this paper, I also found written black and white that it was actually the paper by Christodoulou and Ruffini who showed for the first time that this area cannot decrease. And only some time later, Hawking generalized this result with his area never decrease theorem and proposing his notion of entropy. So why is this relevant for my research interest? Here there is a paper I published just 1 week ago in the Physical Reviewed Journal, together with my colleague Yen Qinong. So we did the following in our paper. So, sorry, one moment. So we took the most general metric for a static and a spherically symmetric black hole. But you can see I'm not writing any restriction on the function f of r. So we considered all the cases of Schwarzschild de Sitter, and Reissner-Nothrum. This means physically that our result, we think, is true both for asymptotically flat or not asymptotically flat spacetime, and also for both empty spaces and not empty spaces. We tried to work in full generality, also allowing for this function h of r to appear, because this function h of r account for some possible black hole distortions and deformations, and there is an active ongoing research project which try to restrict these possible deformations using a newly available gravitational waves dataset. In our paper, we found that a certain quantity, when integrated in the interior region of a black hole, and with respect to the hypersurface volume element, then it will give the area of the horizon. And this quantity depends only on Weyl scalars. So there is the derivative of the Weyl scalar psi2 in the numerator divided by psi2 itself. So our result is fully consistent with the Weyl curvature conjecture for black hole entropy, because our entropy density depends only on Weyl scalars. On the other hand, for the reason I explained before and I called before, we can also say that also the Christodoulou-Ruffini irreducible black hole mass is essentially related to what we did. So there are some mathematical technicalities that you can find in our paper, but we think that the physical result is the following. The Black hole entropy, or in other words, its irreducible mass is, according to our result, a physical consequence of tidal effects. And this is everything that I wanted to share with you in my talk. So just let me conclude by saying happy birthday, Professor Ruffini.
Thank you very, very much for this very nice and clean presentation, and with all the historical development. Congratulations, Daniele.
Thank you.
Thank you a lot for your presence and wishes, and also this progress with Jiangong in your new university, your university, and congratulations again.
Thank you.
Thank you, Daniele. Thank you very much. Is Wenbiao around? I don't see him.
No, I think he spoke already Monday.
Yesterday, yesterday he said a few words, but here I have a technical talk today, but I don't see him. So, okay, so we go ahead. Soroush.
Yes, hello to everyone.
Are you ready?
Yes, I am always ready.
Good to see you.
Good, good.
Okay, can you see my screen now?
I see you.
Yes.
Yes, also the screen, yes.
Okay, nice to see you guys, but virtually, and of course I cannot see your faces, but it's good to have opportunity here to share some memories and also talk a few words about some of my recent works in the boson star and dark matter. So here you can see one of the picture that I had during my PhD period, when for the first time I met Professor Ruffini in, I guess that was in 2015, when I went to the Marcel Grassmann, and then I connected to Professor Ruffini and went for a visit during my PhD to ICRANET, which was, I can say that was a golden period in my career, and I learned so much from Professor Ruffini, from both the scientific side and also in the case of humanity. I think I learned a lot from Professor Ruffini, and exactly that was an important period in my life, and I think this gives so much benefits in all the way in my scientific career. You can see here, I remember here the Professor Ruffini was explaining his model to us for the first time, and he was talking about the different period of the GRB and also the detail of his model. And in that period, actually, I had several experiences in working with the data of the GRB and be familiar with this amazing phenomena, and also the detail of this the model of the Professor Ruffini. And I had this opportunity to collaborate on several papers with Professor Ruffini and his group, and also I found so many good friends during that period, and from different nationality. That was very good for me, because the ICRANET was an international organization, and I had the chance to meet everyone from different nations and different cultures. And that was good from both of the scientific and also, as I said, cultural and political and everything that you can imagine. Here also you can see one of my talk in the Marcel Grassmann meeting about the polarization of the gamma ray bursts when we talked with Professor Ruffini, and he told me that this will be very important subject in future. And actually now we can see that this polarization feature of the gamma ray bursts are very important. And afterwards, the Professor Ruffini had a visit to my university, and he established the Ikranet Esfahan Center, which is now active. And after my PhD student and also my PhD period and having a postdoc in IPM, I come back to Isfahan, and now I am a professor here. And we have this Ikranet Esfahan, and also we are in tight connection with Ikranet Center in Pescara and Ikranet network. And this is one of our great meeting which we had in 3 to 5 November of 2021. As you can see, we had a great meeting and having so many prominent speakers, and we discuss about different topics in relativistic astrophysics. Now, I would like to talk about one of my recent works on in connection of boson star and dark matter. Actually, our works is based on the seminal works presented.
J'arrive pas.
Yes.
Je suis la diététicienne. Vous vous souvenez, on s'est vu à l'USIC.
Oui, oui.
Je reviens juste vous voir pas très longtemps, juste pour savoir comment ça se passe.
Shall I continue, Jorge? Okay, can you hear me now?
Yes, I can hear you.
Okay, sorry, I hear some voices. So let's continue. Here you can see the one of the very important work on the boson star in 1969, when Professor Ruffini and Bonazzola presented that very important paper on system of self-gravitating particle. And this was the first moment that the concept of the boson star established. And actually, you can see nowadays the bosons and boson stars are becoming very important and hot topic in the community. You know, the concept of the bosonic object first proposed by the Wheeler, and that was, he called the geons. And actually the Wheeler's solution were unstable, and the solution that presented by Professor Ruffini and his colleague actually was a stable mini boson star object. And then in another work in 1983, they tried to explain the halo of the dark matter based on this fermionic and bosonic particle. And actually, they tried to connect some particle nature and quantum nature of the particle to some large scale behavior of the dark matter in the galactic halo, and also in the core of the galaxy. And here you can see his this boson star object. Since in bosons we don't have this Fermi pressure, the only pressure is coming from the Heisenberg uncertainty principle. And here you can see with the very light boson with the mass equal 10 to minus 10 electron volts, you can have a solar mass object, and this is very important. And what Professor Ruffini proposed in his work was some mini boson star object. And here you can see when you add the self-interaction between bosons, you can get the maximum mass around 10 solar mass with the mass equal 100 MeV and a coupling, self-coupling constant around, around 1. And this is now very important because we have so many observation of some objects which has some behavior similar to the black holes, but their mass could be in this mass gap region. So the boson stars are very good candidates that can mimic the black hole behavior. And actually, Professor Ruffini and his group presented a model on the fermionic dark matter, which called RAR model. They tried to explain the core of the galaxy by the fermionic dark matter instead of assuming the black hole at the center of the galaxy. And they tried to explain both the short range and large range behavior of the dark matter. And this is very important. But coming back to what I did recently, we discussed about possibility of the boson star and self-interacting bosons behaving as a, some compact object and mimics the behavior of the black hole, and also to have some mixture of the bosons and fermions as a some new object, which we call them dark matter admixed neutron star. Here you can see my colleagues, and here you can see our paper and also some presentation about this work, which the last one was the presentation in Pharos meeting, which is now going in the Sapienza University. And here you can see the new class of the object we introduced. These are some mixture of the bosonic dark matter and the fermionic dark matter. You can see here different configuration that bosonic matter can go around the star, having something like the halo around the compact object, and can go to the core of the object and behave as a dark matter core. And in our work, we consider the different observational consequences of this new type of the object. And recently, we consider the micro lensing of this object and the effect that they can have on the light ray trajectories. And this is very important because they exactly can mimic the black hole behavior, and also you can have a big boson star at the core of the galaxy to have some to mimic some supermassive black hole effect, and also they can behave as solar mass black holes. This is very important. And this here you can see also we consider the I don't know if you can see, okay, here also you can see we consider in a recent work the effect of this dark matter around the star on the self-light bending. You can see here there is a project in NASA which called NICER, and they tried to simulate the gravitational potential of a star by using the light bending around this object. And here you can see if the visible surface of the star increases, actually you could have the high compactness of the object. And here you can see if you don't have gravity, when a bright point goes, behind or line of sight, this disappears. But if you consider the light bending, if this light spot goes behind, or line of sight, you can see also the flux coming to you. What we did recently was considering the effect of this dark matter admixed star on the light bending, and we tried to see how we can discover this new type of the object. Here you can see some of our new result, and I finish here, and here you can see my birthday gift to Professor Ruffini. I don't know, Professor Ruffini, are you seeing
Yes,
here?
I am seeing this beautiful, this is the bridge of Isfahan that you have in the image.
Yes, actually,
And,
this is
yes,
that big square in the Isfahan. This is a traditional play or game. You remember there was a big square in the Isfahan.
yes, definitely.
Yes, and in around, let's say 500 or 600 years ago, the people was playing there by the horses, and
Yes.
and that was some playground, and the king was sitting here in the right and looking at this game, and actually this here I can see show you these things, and this is home. This is human made. This
Yes.
paint is by hand, and this is by a special wood, and this is
Beautiful.
was using to collect the pens. I will give you this, and you can put your pen there, and I wish you all the best for your birthday, Professor Ruffini.
Thank you very much, Soroush. Thank you for this scientific presentation and bringing us to the world, the dream world of Isfahan. It will be always in my heart and memory, and of course I will keep in touch with our center in the university. Give my best to the president and to everyone there, and keep working and educating people around you, and say hello also to the director of the observatory.
Thank
Sure.
you. Thank you, Soroush. Thank you, Soroush. Yes, I would like to thank you also for this presentation, and to mention some of these common topics. So I would like very much that we start to speak about on the problem of polarization. So I will be in touch about that, and also on any progress on compact star physics. So it was very good to see this presentation. Thank you very much. So Professor Wenbin Lin is around. Yes, I saw him in. Yes, Wenbin Lin, Professor Wenbin Lin, are you online? Professor Wenbin Lin. See if there is any problem, because I see him here. He is connected.
Hello, Wenbin. He's just responsible for the physics department in a university in China, in the middle of China, and we are looking very much to collaborate with him. Hello?
Hello. It seems he just went out for a while. I don't know. But anyway, so Professor Wenbin Lin, he was supposed to speak about coordinates in general relativity, time from perihelion to aphelion, and let's see. Wait a moment. If he shows up. Maybe the people from Pescara, did you get any message or any email from Professor Wenbin Lin? Sir. Well, anyway, so well, was our last speaker of this first part of the program. So the timetable, morning session starts at 9 a.m. So in 15 minutes, with Professor Bin Zhang. That I don't see him yet here. Connected? No, Professor Bin Zhang is yes.
I'm here. Can you hear me?
Oh, great. Yes. So great. So in 15 minutes, now it's 8:45. So we are supposed to start 9. So right. So we take
So we are using the same Zoom link.
So we are no, we are just wait, and we will start at 9 as we follow the program. Professor Zvipiran is here with us in this. He will share the morning session. So we are ready, but we wait for 9 a.m. Okay.
Okay.
Good. Thank you.
Thank you.
Zvi. If Zvi is there, we can chat a moment. Jorge, I'm coming to the center, to the villa around 2 o'clock today.
Oh, good. So looking for the steam.
Oh, there is Wenbin, no sound.
Yeah.
Yes, we see him connected, but there's no audio, no video.
Yeah. How do you feel?
Very well, and feel much better. And by 2 o'clock, I should be coming and look forward to discuss with you and Natalie, because I think we have gained with Natalie a much deeper understanding. She's still there, yes?
Yes, she's here.
Yes, good. I have a lot of discussion with her and with Zvi. And of course, with Jorge, because you are the key to tell us more about. I look very much forward to this discussion. And I'm happy I feel much better.
We get it when you feel better. It will be great to see you here.
Yes.
So,
Oui, vas-y.
Donc tu vas mieux.
Oui, beaucoup
Tu te
mieux.
sens mieux.
Oui. beaucoup mieux.
Qu'est-ce qu'ils disent, les médecins?
Euh,
Ils vont te garder.
non, 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 ça va. À 2 heures l'après-midi, je sors.
Ah, pas
Hello?
d'accord. Allô? Ah. Somebody's calling.
Yeah. Can I do a presentation in the afternoon?
In the afternoon.
Yes.
Wenbin, you can speak now.
Yes, you can speak now. We
You
have,
can speak now, Wenbin.
yes.
Yeah. Previously I think I'm not ready for the presentation, so I did not make the PPT. Is it okay just to use my papers directly?
Yes.
Okay, thank you. First, I would like to say happy birthday to you, Professor Ruffini, again. Yeah, thank you. Yeah, thank you for inviting me to present some of my work. Yeah, let me share my papers.
Okay.
Okay, let me see. Can you see my? Can you see?
We don't see your screen.
It's okay. My screen.
No, we don't see it.
Oh, let me see.
Okay, now we see it.
Now we see.
Okay, thank you very much. Okay, yeah, this is my our recent small paper discuss the coordinates in general relativity. We use the example the time from perihelion to aphelion. Yeah, with a coordinate transformation, the Soroush metric in the standard coordinate can become the other one in the concealed coordinate. In this work, we formulate the test particles motion under these two coordinates and show that the calculation results for the time from the perihelion to aphelion are different. Since the time from the perihelion to the aphelion of the celestial body is an observable quantity in astronomy, this example demonstrates that the solution achieved in a specific coordinate may not be the final answer to the investigated problem. Even the solutions are formulated in terms of the physical quantity, such as the orbital energy and angular momentum. This solution should be mapped to the observer's reference frame before being compared with the observation. However, this mapping step has always been missing due to the misunderstanding of general convenience. Okay. In general relativity, it is believed that the coordinates themselves have no physical meaning and the theoretical predictions for the observable quantities are coordinate independent. Therefore, the coordinate transformations have frequently been adopted to simplify the gravitational problems. And finally, the theoretical solutions obtained in the specific coordinates are taken as the final answers to the investigated problem. For example, Boson and Will illustrate that the solutions for the deflection of light from -infinity to infinity in the Soroush spacetime are same among the standard isotropic and harmonic coordinates. In a paper entitled as the Soroush metric is coordinate stripping, the author shows that the coordinate can be arbitrarily chosen and the proper choice of coordinates can greatly simplify the problems under investigation. However, the premise for the statement that the coordinates do not matter is that we have to map the theoretical solution in the specific coordinates into the observer's reference frame. This mapping can be thought as the gauge invariant construction of the theoretical predictions for the observable quantity. If we do not perform this step, the achieved solution may be dependent on the coordinate in which the calculation has been carried out and may not be the final answer to the investigated problem, even they are formulated in terms of the physical quantity. In this work, we will take an example to illustrate this important issue. Since the celestial bodies can be observed in astronomy, for example, the planets revolving around the sun, the time from the perihelion to aphelion of the celestial body is an observable quantity. For convenience, we call this time as the perihelion to aphelion time throughout this paper. We study the motion of the test particle in the Schwarz space-time and show that the theoretical solution for this time are coordinate dependent. We consider the Schwarz metric in the standard coordinates and the Kerr field coordinates. In order to see the difference of the theoretical solution between these two coordinates clearly, we followed the procedures given by software to derive the second post-Newtonian solution for the test particle's motion. The analytical solutions are formulated in terms of the physical quantity, the orbital energy, and the orbital angular momentum, as well as the gravitational source mass. Okay, now let's first introduce the Schwarz metric in the standard and Kerr field coordinate. Schwarz metric describes the external spacetime of a static and spherically symmetric system. It has different form in different coordinates. In the standard coordinate, the Schwarz metric can be written as equation 1 in this form. In the paper, the neutral units with G equals C equals 1 are used. Mass is M is the mass of the gravitational force. Then, taking the following coordinate transformation, T prime equals T minus 2M, log R minus 2M. We will arrive at the Schwarz metric in the Kerr field coordinate as follows. Here we have rewritten the T prime as T. Now we will present the second post-Newtonian solutions for the quasi-Keplerian motion in the standard and Kerr field coordinates separately. Since the Schwarz space-time is spherically symmetric, we can only consider the test particle's motion in the equatory plane. The particle's motion vector can be written as equation 4, where y being the azimuthal angle. In order to compare the solution between the Schwarz standard coordinate and the Kerr field coordinate, we derive the solution to the second post-Newtonian orders. That epsilon and J denotes the orbital energy and angular momentum for the test particle. The second post-Newtonian solution for in these two coordinates can be written as follows. Yeah, this is for both coordinates. The formulation here are AR and ER equation 5, 6 to 7 are same, but for the quasi-Keplerian equations are different. For the standard coordinate, this equation is written in equation 8. However, for the Kerr field coordinate, the quasi-Keplerian equation has to be written in equation 9. In equation 9, there's additional 1.5 post-Newton's term here. For the constant orbital parameters are given by the energy and angular momentum J. So these two equations, these two solutions between these two coordinates, only difference is in the equation 9, the last term. So for the above formulation, we can see that also the solutions for the test particles orbit and in the standard coordinate in the Cartesian coordinate are same. The Quasi-Keplerian equations, which characterize the time evolution of the test particles motion, are different. The Quasi-Keplerian equation in the Cartesian coordinate has an additional 1.5 post-Newton's term of this one. So now we can compare the solution for the perihelion to aphelion time between these two coordinates. For convenience, we denote this time in the standard coordinate as P2P_s, and that in the Cartesian coordinate as P2P_ks. Substituting the perihelion condition F equal E equal 0 and the aphelion condition F equal E equal to pi into equation 8 and 9 to the 2pn accuracies, we have the time from the perihelion to aphelion in these two coordinates. In the standard coordinate, the result is given by equation 18. The result in the Cartesian coordinate, the result is given by equation 19. It can be seen that the solution for the perihelion to aphelion time based on the Cartesian coordinate is different from that based on the standard coordinate, and they cannot be obtained from each other via the coordinate transformation given by equation dynastically. Good. Considering a simple scenarios in which the observer is static in a asymptotically flat region, which solution should be used to compare with the measurement of the time from the perihelion to aphelion? The example presented in this work illustrates that the solution achieved in a specific coordinate may not be the final answer to the investigated problems, even they are formulated in terms of the physical quantities, for example, the orbital energy and angular momentum. As mentioned in the introductions, we have to construct the coordinate-independent solution for the observable quantity. In other words, we have to project the solution in a specific coordinate into the observer's reference frame before being compared with the observation. Good. However, due to the misinterpretation of general convenience that the observable quantities are coordinate independent, it has seldom been checked if the achieved solution are dependent on the employed coordinate or not. In the literatures, the theoretical solutions for the gravitational problems have usually been achieved in a specific coordinate and taken to be compared with the observation directly. This is an example I do not want to present in detail. On the other hand, the coordinate transformation have frequently been employed for simplification in solving the gravitational problem. This is another example for the derivation of black hole theorem. In the derivation of black hole theorem, people take some coordinate transformation and then solve the Einstein field equation and arrive at the result should be the metric Schwarz matrix. But how do we know outer performing this coordinate, the solution is coordinate independent. I mean, the solution is still corresponding to the original problem because this work has shown a clear example to show that the solution in a specific coordinate may not be the final answer to the involved problems. So taking coordinate transformation to simplify the problem is okay, but we have to check the finally the solution achieved in this specific coordinate should be independent on the coordinate which is used for the calculation. Yeah, this is my talk. Thank you very much for your attention. Thank you.
Thank you very much, Wenbin Lin, and we look forward to see you here in July. Okay.
Okay.
Thank you in person. See you soon. Bye.
Thank you very much. Okay.
Thank you. So we now can start, and we switch Sherman now invite Professor Tripiran here to we share the morning session. Professor, the microphone is open.
Good morning and welcome. It's a pleasure to open this morning session and to invite Bing Zhang. I guess from the time that we are talking, you are now in Beijing and not in Las Vegas, but it's a pleasure to see you wherever you are.
It is in
we will be talking, I understand, we will be talking about fast radio bursts, which is one of the most exciting discoveries of the last decade and how we understand them. So please go ahead.
Thanks, Tsui. Let me share my screen. All right, can you see the screen?
Yes, very well.
Okay, I'll start to say happy birthday to Remo.
Thank you so much.
Colleague and good friend. And so we had relationship connection for so many years. And so these are just the nice memories of the previous 4 Marcel Grossman meetings from Stockholm and from Rome, and last year it was online. And this one actually was the 3 years ago, probably the last GRB meeting before the pandemic. And actually here we have Remo, we have our chair Tsui, and myself is sitting next to you guys. And we had a nice time together. And Remo, I don't know whether you remember, during that meeting, it was your birthday, 3 years ago, 77th birthday. So here was the picture. So this was the happy birthday to you back then. And here was the big cake. So hopefully you have a even better celebration this year. Unfortunately, I have to miss it.
Thank you. Thank you.
Happy birthday again.
Thanks.
Okay, the physics of fast radio bursts. So our communication with Remo was on GRBs, but I'm going to talk about another type of the cosmic transients and mysterious transients. They're called fast radio bursts. So I start with introducing some of the observational properties, because in order to understand their physical processes, we need to know what is going on. And there are many review papers, and my talk is mostly based on these 2 review papers I wrote recently. And so we'll start with the temporal properties. So there are short duration, only milliseconds, and they have internal structure. So initially people just saw 1 pulse, but later some bursts have multiple pulses. And they have repeaters and non-repeaters. So at least some FRBs, they repeat many times. And some of them are very active. They can make thousands of bursts within a month. So even though most of them are not observed to repeat, based on some arguments, maybe the majority of them are repeaters, simply because the non-repeating sources like supernova, their event rate is not high enough to accommodate FRBs. Indeed, some of them have very high repetition rate, but some others actually people followed up many times but haven't found another burst yet. And observationally, there are also a little bit evidence showing that there could be observational dichotomy. For example, repeaters are longer than non-repeaters, but we don't see a clear cut yet. And there's also one repeater had a 16-day period, so very mysterious. Another one probably had 157 day that is not firmly confirmed yet, but looks like some of these repeaters have this very long periodicity. And in terms of spectrum, the frequency that there have been detected in this frequency range, the spectral shape could be a power law, but for repeaters, they look like a Gaussian-like, they're narrow spectrum. And very interestingly, some of the bursts showing this frequency down drifting, which means the higher frequency pulses arrive earlier and the lower frequency pulses arrive later. And this was the recent fast observation of one of the repeaters. You can see very complicated morphology in terms of pulse profile, in terms of this temporal spectral evolution. And in terms of polarization, it seems like most of them have very high polarization degrees. Some of them are consistent 100%. Circular polarization has been observed in a small fractional bursts, but very interestingly, so this is the linear and this is the linear, there's a circular. If we do the Stokes parameter, even though they have higher circular polarization, they have a slightly lower linear polarization, but when we do the total, it's consistent to be nearly 100% polarized. And they also have large rotation measure, which is a convolution of the density and the B field along the line of sight. And very interestingly, this RM actually show secular and sometimes short-term variations. This is a recent fast observation of one repeaters. You can see this RM actually goes up and down very substantially within a month's time. Polarization angle. So a lot of the sources show a flat polarization angle, which means the magnetic field configuration probably stayed the same. However, in some other cases like this one, you can see that polarization angle actually evolves within the short duration milliseconds. So that tells us some extra information that the B field configuration is more complicated. There's also dispersion measure, which tells us how far away they are, because it is the integration of number density of electrons along the line of sight. And some of the FRBs have been localized and redshift measured. It is consistent with this simple relationship. If we know the redshift, we can know the DM or the vice versa, but there's a large scatter. But in general, it is consistent with the standard cosmology with the Hubble constant and omega b. With the distance, we can calculate the luminosity and energetics. So the typical luminosity peak, isotropic peak luminosity in this range, 10 to the 38, 10 to the 46. Isotropic energy is 10 to the 35 to 10 to the 43. In the GRB standard, these are very small. However, in the pulsar standard, these are very, very large. And of course, we also should consider the beaming factor. And if we consider beaming factor, these numbers should be smaller. And another interesting parameter is called brightness temperature. It is a combination of the luminosity and also the duration. Then it turns out that it's extremely high. This is probably the highest brightness temperature in the universe, up to the 10 to the 36. And these two fields actually are quite similar to each other in terms of questions to be addressed. Are they astrophysical? Are there multiple types? Where are they and what makes them? And there are some breakthrough discoveries, but the pace for in FRB field is much faster than GRB field. So we now know actually what makes them. That was quite surprising because in the GRB field, it took a very long time to figure out what make them. And this is another comparison. So the histogram or GRB papers as a function of time. And for FRB papers, it is scaled down by a factor of 0.4, which means FRB published more papers. And also time is divided by 2, which means FRB field has a faster pace. So so far it is matching the GRB field very well. Based on this prediction, this is a projection, then FRB field should publish a lot more papers. And it's a lot of fun because we are serving as a detective's job. So based on this host galaxy periodicity, so these are footprint, fingerprints, and sometimes smoking guns, we can figure out the crime scene. And what make them, so that this was similar to the GRB field, more than 100 models. In FRB field, there are more than 50 models, and they even have a website maintaining all the models there. But this was like all kinds of probabilities, like wave function. And on that day, April 28th, the wave function collapsed. So we had only one, at least one possibility, so that is magnetars. So basically, we detected one very bright radio burst in our own galaxy, and we know where it comes from. It is come from one of the magnetars, and also there was a X-ray burst associated with the radio burst, and actually the peak times aligned with each other. So this was a major advance in the field. And talking about models now, the FRB models typically have 2 components, and these 2 components can be decoupled. So one is the coherent radiation mechanisms, which means it does not heavily rely on the source. Even if it is not a magnetar or something else, we have to address the coherent radiation mechanism. And another one is the source models. And for the same source model, we can have very different emission mechanisms. So we tend to cut this into different branches. So for example, we can focus on the coherent radiation mechanism. So for coherent mechanism, we also have inside the magnetosphere, or I call it pulsar-like, or outside the magnetosphere in the shocks, like GRB-like. And within these different subcategories, there are also many mechanisms proposed. And for source models, we have models for repeating and non-repeating models, and magnetars, of course, has been proved, but there are many other models proposed. And in this field, people have been doing theoretical investigation in 2 approaches. One is bottom up, start from one mechanism and see how it matches the observations, start from one source model and see whether it matches observations. But the other scenario is top down. So we start with FRB observation and see which one is the best fit to interpret the model. So I'm going to talk about this top-down approach. Or detective's approach. So let's put some general constraints. The first one is the duration and engine size. Just based on the duration alone, one can already say that we should involve neutron stars or stellar mass black holes, simply because the duration times speed of light is of this order, and other objects are much bigger than this. Of course, there have been models proposing white dwarfs, stars, or even AGNs to produce FRBs, but all those models need to have fine-tuned conditions so that the emission region has to be very small. The second one is the energetics, radio efficiency, and beaming. As I already mentioned, these are the isotropic peak luminosity. This is the energy. And one should also consider the beaming factor. However, we should also consider the radio efficiency, because we only see emission in the radio band. There could be emission in other band, actually maybe in the dominant channel should be in the X-ray band, as we have seen in the galactic magnetar case. So the total energetics is actually bigger. And for beaming, we should also consider this local beaming and global beaming. For individual FRBs, probably they have a small beaming angle. However, there might be many mini jets sitting in a much bigger solid angle, and this solid angle may not be 4 pi, because if we consider, for example, a magnetar, a magnetosphere, there might be a solid angle related to the open field line region or something. But within this this big window, we have smaller patches of mini jets to produce FRBs. So in terms of energetics and sources, we talk about one-off bursts. We can use these formula. However, for repeaters, we should also consider, we should add together everything we see in the radio band. And then we start to correct for the beaming, we start to correct for the efficiency, we start to correct for the duty cycle, basically the observing time with the total time. So this is a better way of constraining the sources, energy sources. And in principle, theoretically, we can have magnetic energy, we can have spin energy, gravitational energy, or kinetic energy. But right now, it seems that the magnetic energy or spin energy is playing most important role in producing FRBs, at least for the repeaters. And for brightness temperature, as I already said, it's a huge number. One can also calculate the brightness temperature for incoherent radiation, and it turns out the maximum, even if we consider relativistic motion, like in the case of GRBs, the maximum brightness temperature is only 10 to the 13 K. So this is definitely much greater than that, and one needs to have a coherent radiation mechanism. And in the literature, there are 3 types of coherent mechanisms. In general, we have emission in bunches, antenna, we have plasma masers, we have vacuum masers. So this one involves the plasma instability to amplify growth some modes. And this one is just radiation, get negative absorption and keep amplifying and reach a very high brightness temperature. And in order to see FRBs, so we have to overcome all these absorption processes, for example, induced Compton scattering, or free absorption and synchrotron absorption. So this actually places some limits. For example, you cannot, the FRB source cannot be a very dense region environment. Otherwise, all the waves got absorbed or got scattered and cannot reach us. So if we are talking about magnetars, the magnetar cannot be too young, because the young magnetars are embedded in the very dense supernova remnants. So we need to wait for some time, at least a year or decades to have them become transparent. So these are the other considerations. And for the detailed mechanisms, because we don't know what made FRBs, we just borrow some ideas from the relatives, the two neighboring fields, GRBs and radio pulsars. So from the GRBs, we can have some lessons. For example, GRBs, we talk about relativistic outflow, we have internal shocks and external shocks. And some of these ideas have been used to develop one version of the FRB models. So we can introduce internal and external shocks. But this time you need to really have highly magnetized outflows so that shocks are highly magnetized. So there, the B fields are ordered, and then synchrotron maser can operate and make highly linearly polarized FRB radiation. So this is one model. And the lessons from the radio pulsars, because radio pulsars, we know they can make high brightness temperature radio emission. So this is famous Crab pulsar. You can see in the radio band as compared to the gamma ray band. So there are alignment with the two bright components. in the high energy band, which means the radio emission can come from very outer part of the magnetosphere, either near the light cylinder or even outside the light cylinder, because gamma rays are from there. And we also have radio emission, say like precursor. It is more consistent with coming from the polar cap region. Actually, the majority of the normal pulsars have emission coming from the polar cap region. So the lesson from radio pulsars is that actually we can make FRBs either within the magnetosphere, close to the surface, or near the light cylinder. So there are plenty of methods of making coherent radiation. So in general, there are two types, pulsar-like or GRB-like. So these are involve relativistic shocks, and these involve magnetospheres. And these two types of models have somewhat different predictions. The pulsar-like models have narrow beaming because we have strong B field confine the radiation, confine the particles, and therefore the radiation is also narrowly beamed. And if we invoke shocks, and typically it's quite wide, especially in the magnetized wind, is hard to collimate it. So this model generally predicts a wider opening angle than this one. Radio efficiency, this one is relatively low because from the first principle, the energy goes to the single Shang maser is the only small fraction, typically 10 to minus 4. And this one, there's no prediction, but observationally in the radio pulsars, the radio emission efficiency can be very high. And because of this, the high energy counterpart, this model predicts a brighter one than this one. And in terms of polarization properties, this one, either there's one version, there's no polarization at all. The other version, you can produce 100% linear polarization. However, the polarization angle has to be constant, because in the shock, the B field by definition needs to have nearly parallel to each other in order to make a single Shang maser. And the other model for the involving pulsar magnetosphere, because we are considering line of sight sweeping different parts of the field lines, the opening, the polarization angle can vary, and polarization degree, of course, it is very high because either it's curvature radiation, inverse Compton, they all produce very high degree of polarization. Okay, and these are the observations. The polarization properties can actually serve as a clue. Some of them indeed have flat PA, so this can be interpreted with the shock model or magnetosphere model involving very outer magnetosphere. However, some others indeed show this rapid variation of the polarization angle. Then this can be only understood within the magnetosphere model, and this model is disfavored. And there was also the other property like this one. We use fast to detect more than 1,600 bursts within 50 days, 59 days. And there's energy distribution, very high repetition rate, short waiting time scale. For example, some of them we only need just waited for like milliseconds, another burst came out. And in the shock model, usually after each collision, the B field is already perturbed and plasma is hot. You need to cool down a little bit before another burst is produced. So this peak, typically 100 seconds, is consistent with that scenario. However, this peak is difficult to accommodate within the shock model. And one can also work out the total energy. So based on what we observed in the radio, consider beaming, efficiency, and duty cycle. So within 59 days, the total energy emitted, this is already assuming global beaming 0.1, is almost 10 to the 46. If the beaming angle is beaming fraction is smaller, then it's already more than 10 to 46. However, a magnetar dipole total energy is only 47. So this is assuming eta equals 10 to minus 4, which is the shock model. So this tells us if the shock model is operating, then we run into a efficiency, the energetics problem. So either the efficiency should be much higher, which means it's not from the shocks, it's from the magnetosphere, or maybe the total energy budget is larger than this, then we have to consider more extreme central engine than magnetars. And frequency downdrifting, as I said, observationally, high frequency waves arrive earlier and low frequency wave arrive later. This is also consistent with the magnetosphere model. If you have a bunch moving slide along the field lines and doing curvature radiation, we always see high frequency wave first and then low frequency later. Okay, and let's get back to this magnetar. So we did find one FRB from this magnetar. Then what process made the magnetar, made the FRB? So there are many suggestions, and these are very briefly some of our recent suggestions. So this one was done with Wenbin Lin and Pawan Kumar. So we have presumably there is a cross-cracking or something launching some alpha waves, and these alpha waves will, when they propagate in the closed field line regions, will just heat it up and make X-rays. If it propagate in open field line regions and at certain radius, it will reach the charge deficit region, and they start to develop parallel E field and make bunches and curvature radiation to make FRBs. And another scenario, which I proved recently, instead of doing curvature radiation is not very efficient, but inverse Compton can be more efficient. So suppose the same oscillation can send out some low frequency waves, and these waves can be efficiently scattered to FRB frequency, either in the open field line regions or outside the magnetosphere from the current sheets. There was a recent paper by Andrei Biloborodov saying that FRBs produced inside the magnetosphere cannot escape because the scattering cross-section is very large. And that was based on the assumption that the magnetosphere is static, the particles are not moving. Recently, Yuan Hongqu, my student, Pawan Kumar, and myself, we investigated this and we consider more realistic situation like the open field line region. The particles are actually moving outwards, and when the waves comes over, actually the optical depth becomes much smaller. So we give, and also the wave is so strong, the B field will get nearly aligned with the direction of the waves. So when we consider these two factors, we see that the FRBs can be transparent within the magnetosphere, and as long as gamma P, the plasma is moving relativistically. Another interesting observation using FAST was we monitored the source even before the FRB happened, and Fermi detected 29 bursts, but there was no FRB at all. Then that FRB came out that it was associated with another burst. So it means that such kind of associations are very rare, which means not every, actually the majority of the gamma ray X-ray bursts are not associated with FRBs. And this is very interesting. So one possibility is the FRB is much more narrowly beamed than X-ray bursts. If that is the case, then we should, I call something called slow radial burst, which is the off axis, the duration is longer, the flux is lower. So we should expect something like this from the magnetars. So there are some candidates, but so far we don't have a very strong constraints on this yet. So this could be a way of testing whether FRBs are beamed. Open questions. these are three widely discussed questions in the field right now. Where is the FRB emission generated, whether it's magnetospheres or shocks, and what is the coherent radiation mechanism? So these are the emission part, and this is the source part. Are there engines other than magnetars that power FRBs? If so, what could be the plausible sources? These are for repeaters. And finally, are there genuinely non-repeating FRBs? If so, what could be the plausible sources? So these are two extreme versions of the source models right now. This is the most conservative version because we know that magnetars can make FRBs. So one most conservative scenario is all the FRBs are made by different types of magnetars. The active repeaters could be made by special magnetars, newborn magnetars from long GRBs, superluminous supernovae, neutron star mergers, and the regular repeaters or non-repeaters are made by regular magnetars. So this is magnetar make all scenario. This one is most speculative one. The still FRBs can have repeaters and generally non-repeaters. And within the repeaters, besides magnetars, we can have something else. And there are also generally non-repeaters. So this is more exciting. I don't believe that there are 50 different ways of making FRBs, but if we only have one way of making FRBs, probably we underestimate the creativity of nature, because in the field of GRBs and supernovae, we also have like multiple physical types. So hopefully we'll eventually find some other non-magnetar made repeaters and even genuinely non-repeaters. So one very interesting prospect is gravitational wave connection. So these are several different scenarios. One possibility is that the two neutron stars, even decades
to little bit over time. So can you try?
Okay, so this is last slide. So the magnetosphere interaction can make repeaters. And also after the merger, we produce a supramassive neutron star collapse to a black hole and could emit an FRB. Okay, so I'll stop here and take questions. Sorry for the delay.
No.
Thank you very much.
Thank you. So thank you very much. Are there questions from the audience or from the listeners on Zoom?
I have one. Question? I have one. Yes, thank you. Is there any lower limit to the population? I mean, the rate, because that could certainly would constrain very much all these progenitor. For example, the magnetar one that could be very constrained, or at least the progenitor of a magnetar.
Right. So we should talk about the rate density, so number per unit time per unit volume. And it depends on the luminosity. If we actually consider the low luminosity FRBs similar to the one we detect in our galaxy, then the number can go up to 10 to the 7, 10 to the 8th per gigaparsec cube per year. And recall that supernova only have 10 to the 5th. So that's why people are saying that there's no way that these catastrophic progenitors can do this. But if we only focus on very bright ones, let's say we cut this luminosity up to, say, 10 to the 42 ergs per second and up, then probably you can get a smaller number and accommodate some of these models. So the bottom line is, in order to make that argument, you have to say that the brighter ones are different from the fainter ones.
Thank you.
This is Sancho. May I ask a question?
Sure, please go ahead.
Oh, yeah, Bing. Good to see you again. Yeah, interesting talk. I have a question about if you measure polarization from X-rays or short wavelengths, photons from magnetar, then because of vacuum by refrigerance, there must be some kind of the polarization effect. That is an undeniable evidence. So is there any possibility of measuring polarization for
Yes,
X-ray or short wavelengths?
Definitely.
Photons from magnetar?
Yes, definitely. If we can measure polarization, for example, during the FRB, there's simultaneous X-ray burst, and we can measure the polarization, then one can definitely constrain a lot of things because the magnetosphere model will predict stronger polarization than the shock model. But still, first, observationally, we don't have a detector yet. There are some proposals. I think they're still under construction or in the proposal phase. Hopefully, Polar 2 or LEAP or something like that, when they start to operate, they can detect polarization. Second, even if you detect strong polarizations from the X-rays, then I believe theorists can still create different versions models to interpret the data. So I don't see a clear prediction, say that with such kind of prediction, one way or the other, the model will be ruled out. But it would be very interesting. There should be more constraints, definitely.
Yeah, thank you for your answer. I'll contact you later in person.
Thanks. Yeah.
I have one more question. I recently heard a very interesting talk by Jonathan Katz, so I'm basically repeating what he mentioned there. And he pointed out that within the repeaters, there is no short time scale periodicity as would have been expected from a rotating neutron star or rotating magnetar. So he considered this as a very strong argument against the repeaters originating from rotating neutron stars. He has another model which I don't want to go into, but just I want to hear you answer to the question why we don't see at all any periodicity in the short time scale periodicity in the repeaters.
Yeah. That's a very good point.
Very strong limits on periodicity.
Yeah. I know Jonathan's work. Actually, we did a much even stronger constraint recently. So we had 1,000 bursts in 4 days, and there's no periodicity at all. But that does not completely rule out the magnetar scenario, because the one can have, student did some simulations. So for example, if you have a this beaming angle, the global beaming angle is wide, for example, it is 0.3, 0.4. And then you start to randomly generate these mini jets within this very wide beaming angle, because we don't detect radiation from every period. The period is very short, like 1 second. Then you start to smear up all the signals. So according to her simulations.
Yes, but he points out that the basic periodicity at the bottom will still be observed, even if you try to manipulate on top of it random process. There is enough data to rule this out.
If he has a strict emission geometry, but for the burst, for the burst, like it's not pulsars. These are very energetic bursts, and the burst can easily destroy the ordered magnetic field configuration. And actually, every time the field line configuration can be completely changed. So they do not really follow the strict periodicity window defined by the field lines.
Okay, I think this is one of the interesting keys, because as you mentioned, it is possible that they are completely two different processes that produce FRBs. And I don't think that calling them repeaters and non-repeaters is a good deviation. It's the more is the question of the duty cycle. There are some with extremely high duty cycle and some with extremely low duty cycle, maybe not repeating at all, but there is such a big difference in the duty cycle that this really suggests that even if the non-repeaters are repeating for over a very long period, they are different phenomena from the repeaters.
Yeah, exactly. So actually another interesting simulation we did was to simulate the observed number ratio between repeaters and non-repeaters by assuming what you just said, to assuming a variety of these duty cycles. And then if there are indeed non-repeaters, generally non-repeaters, under the simplest condition, this observed ratio may reach a peak because as time goes by, we start to see all the repeaters in the sky, and the non-repeaters, the rate is the same, then we keep detecting non-repeaters. Then observed fraction becomes, can reach a peak. But there could be complications in consider the evolution of the rate, and those things and become more difficult. And the peak time also depends on parameters. It could be up to 1,000 years. If that's the case, then it's hopeless.
Okay, so thank you very much. We are running out of time, actually slightly over time by now. So we'll thank you, thank Zhang again. And we'll go now to the next speaker, which is Lorenzo Amati.
Hello, Zvi.
Hello, nice to see you, and congratulations. I heard that we know that the Zeus went to the next phase now in the second round. So congratulations on that, and good luck with this to all of us in this second attempt.
Thank you very much, Zvi. So it's my pleasure to see you again, and of course, best greetings of happy birthday to Remo. I'm very sorry that I could not come. Augurissimi Remo. So, and many thanks for inviting me to provide this short review on gamma ray burst. So the perspective use of gamma ray burst for cosmology, the properties and expected impact of the so-called Amati relation, and of future mission, especially I will mention about Theseus, that as all we hope would be really a great achievement for the gamma ray burst and multi-messenger community. So let me, okay, so of course we know very well gamma ray bursts, especially long gamma ray bursts, are the most luminous phenomena in the universe, with huge released energies and luminosities, and a redshift distribution extending up to at least 9 or 10, which means to the very early epochs of the universe, when first stars and first galaxies were forming, the universe was starting to be recognized. So really, we have this probe actually connecting us to one of the most interesting phases and still to be fully understood phases of the universe. So the use of gamma ray burst for cosmology actually comes in two main flavors. The first one is a right to exploit gamma ray burst for investigating the early universe, as I just mentioned. The other one, which is the most debated, but also very toughly investigated, is to use gamma ray burst for measuring cosmological parameters and hence investigating the properties and evolution of dark energy, or in general, testing alternative cosmological models. And there is where also the Amati relation comes to play. So let me focus first of all on the use of gamma ray burst for investigating the universe. As you can see in this popular sketch on the right, gamma ray bursts are bridging us right to the so-called cosmic dawn. So after the first tens, 100 million years of the universe, when first stars, first galaxies are forming, the intergalactic medium is starting to be reionized. POP3 stars, for instance, are expected to be there. And here we want to exploit again the huge luminosity gamma ray bursts, but also their association with the explosive death of very massive stars, and so also to exploit the capability of gamma ray bursts to trace the star formation rate evolution up to these very early epochs. So to give a best flavor of the potentialities of gamma ray burst, if we look at the picture on the bottom on the left, this is the picture taken by a very sensitive telescope of the near infrared afterglow of the farthest away gamma ray burst ever detected at the ratio of 9.2, 9.4, which means that it is true that at this very early epoch, we are talking about a few 100 million years after the Big Bang. There have been nowadays in the recent years detections of very bright, very massive galaxies, several of them detected through lensing. But instead here, gamma ray bursts give us the possibility of directly detecting the explosion or the consequence of the explosion of a very massive stars in the so early epochs without any gravitational lensing or any other effect. This is simply also independent on light independent on the mass or the luminosity of the galaxy. So here, this shows us how powerful are gamma ray bursts for this. And for instance, getting a statistical sample of very redshift gamma ray bursts, so redshift higher than 6, which means the first billion years after the Big Bang, we can, with a statistical sample of gamma ray bursts, several tens or 100 gamma ray bursts at these redshift ranges, solve the large uncertainties that, as you can see on the right, still affects and will affect also in the next years the star formation rate evolution beyond the redshift of 6 or 7, where you can see these shaded regions are the star formation rate evolution extrapolated from the still small number of very redshift galaxies that have been detected. So these require several assumptions on the faint end of the luminosity function of very early galaxy and so on, which is very difficult or very uncertain to be determined with current or even future optical near infrared facilities. And the red crosses show what gamma ray bursts could provide in the future with, again, tens of high-redshift gamma ray bursts detected and identified. Even more impressive is this picture on the right, where you can see that after the afterglow fades away, as shown on the top left, so after weeks or months, if we point a very sensitive telescope to the direction of the farthest away, so very high redshift gamma ray burst, with the Hubble Space Telescope in this case, you can see actually nothing. You can see nothing. So we know that in these directions, at these redshifts, there are very redshift galaxies that only thanks to our capability of detecting and localizing the gamma ray burst, following it in the optical near infrared wavelengths in a very efficient way. But otherwise, we would never know about these galaxies that are below the detection threshold of even the most sensitive optical near infrared facilities. So this means that gamma ray bursts provide a unique channel for detecting the bulk of the population of very high redshift galaxies, low mass, low luminosity galaxies, that may be the bulk of the population of primordial galaxies that are also expected to host the bulk of the star formation in the early universe phases. So really, gamma ray bursts provide us a unique tool for, let's say, detecting, identifying, localizing invisible galaxies below the detection threshold of even the larger facilities. And this will be true even in the future with JWST, LT. Of course, they will improve substantially with respect to current facility, but still, they will not be capable of detecting by themselves. There will be no survey in the optical sensitive enough to allow them to point or to detect directly this, most of these galaxies. But moreover, in addition to detecting and localizing these galaxies, if we can do absorption spectroscopy on the fading afterglow before it fades away with a sensitive telescope, through absorption spectroscopy of this galaxy, we will not only know that they exist, where they are, how many they are, at what ratios they are, but also their metallicity, the neutral hydrogen fraction, and also the properties of the intergalactic medium around them, which means also the capability of studying the evolution of the metallicity in the early universe, the evolution of the intergalactic medium, and so of the cosmic ionization process, and again, complementing in a very important way the understanding of the star formation rate evolution, which is in turn fundamental for assessing if, for instance, first population of stars were capable of reionizing the universe, also taking into account the ultraviolet photon escape fraction of their host galaxy. These capabilities of gamma ray burst are very well known by the cosmology community, but here a main issue is that our capability of detecting, localizing, and identifying high-energy gamma ray burst is still very poor, despite the efforts in the last 25 years of many space and ground facilities. So we are still stuck with less than 10 gamma ray bursts that has actually higher than 6. So the main aim of next generation, so I mean for the 30s, for the next decade, gamma ray burst missions, one of the main objectives is actually fully exploiting this capability of gamma ray burst for investigating the early universe and more in general for cosmology. I will show also later about the other aspect of using gamma ray burst for cosmology. In addition, of course, to multi-messenger astrophysics, transient energy sky, and operating with a great synergy with next generation very large facilities through the whole electromagnetic domain. Here I focus, I give as an example the Theseus mission that we already mentioned at the introduction with 3, which stands for Transient High Energy Sky and the Universe Surveyor, which is a mission concept developed by a large European community with contribution from the worldwide gamma ray burst and time domain astronomy community. This mission concept was selected in 2018 by ESA as one of the 3 candidates as M5 mission for a launch, a medium-sized mission for a launch in 2032. The phase A study was very successful. At the end, ESA decided to go for a mission to Venus, so a completely different kind of science. But the study was so successful, allowed us to progress importantly in the assessment of the scientific requirement and of the mission profile, the instruments development, and so on. And so now we reproposed, we are reproposing Theseus to ESA for the next opportunity for a flight in 2035. Here you can see the key persons and consortium of the mission, and this is the main concept, which is also, again, a general concept that is being investigated not only in Europe, but also in USA, in Japan, and China. So it is a general idea, which is to overcome the current limitation that, again, are limiting our capability of detecting and identify high-energy gamma ray burst by improving our capability of monitoring the sky, extending the current capability of gamma ray burst monitor down to soft X-rays and up to 510 MeV. So this would allow, especially the extension down to soft X-rays, to detect much more high-energy gamma ray burst, in addition to X-ray flashes and the luminous gamma ray burst and so on, and join it with the capability of a fast follow-up in the near infrared on board. So with in a Swift-like manner, carrying on board, in this case, a near-infrared telescope, not an X-ray telescope like Swift, and with slewing capability of the spacecraft of the order of the minute. So these joint capabilities will allow us to go from the current situation. This is the distribution on the left of gamma ray burst luminosity versus redshift, and on the right, you see the distribution of gamma ray burst as a function of redshift in this cosmic cone context. As again, you can see that above this dotted line, which is a redshift of 6 or first billion year of the universe, we still have very few gamma ray bursts identified there. And with a machine like Theseus, this is what we expect to obtain with only 3.5 years of operation. So really a giant leap that will allow us to fully exploit eventually gamma ray burst for cosmology. But of course, not only. I'm focusing on cosmology here. Of course, Theseus would work and a mission like Theseus in great synergy with the near-infrared optical facilities of the future, which would complement and enhance substantially the scientific electronics used for investigating the universe. For example, of course, as you can see on the left, one could do very fine near-infrared afterglow spectroscopy with the ELT or TMT telescope, or even exploiting the synergy with the other ESA mission Athena, expected to fly in the second half of the 30s, doing X-ray spectroscopy of the circumburst environment. Now let me focus on the other side of the use of cosmology of gamma ray burst, which is, as I anticipated, trying to exploit again their luminosity, their ratio distribution, and other properties, spectral properties, luminosity correlations for complementing other probes in studying the expansion rate and evolution of space-time. So why, first of all, we would like to have one more probe? We already have the type 1a supernovae, clusters, DAO, of course, the CMB. Well, as you can see on the left, all these probes have different sensitivity to the cosmological parameter. Let's say in the standard lambda CDM scenario, in this classical omega m, omega lambda, plots of density of matter with respect to density of, let's say, cosmological constant or dark energy, for instance. They provide different orientation because they have different ratio distribution and they are based on different methods. If we consider, in addition, each of these probe is affected by its own systematics. For instance, a famous case of type 1a supernovae, which like gamma ray burst are not standard candles by themselves. They can be standardized through a correlation between peak magnitude and let's say the shape or the decay time of the light curve, which is the Phillips relation, as you can see in the plot on the right. And here there is a list of possible systematics that may affect this standardization and hence include systematics in the determination of cosmological parameters with type 1a supernova. So by putting together more cosmological probes, we put together different sensitivities to the cosmological parameters and reduce the impact of systematics. But what we are aiming at, again, we are now clear that all probes are converging to a lambda CDM model where density, which is mostly flat, density of matter is around 30%, and so 70% is still the unknown cosmological constant, dark energy, or other explanation. What we would aim with a probe like gamma ray burst, which has the unique property of extending the Hubble diagram, for instance, to very high redshift, so much beyond type 1a supernovae or baryonic acoustic oscillations, or even the studies that will be done through the Euclid mission, for instance. So this is also why also AGNs, very high redshift AGNs, are investigated on this respect. So the aim is to have an expansion of the study of cosmological parameters, dark energy, cosmological constant, up to a redshift of 8, 9, or 10, so to provide better clues on the possible evolution of dark energy, for instance, or allowing to test alternative cosmological scenarios. So the most investigated tool, there are several, there are also other tools, correlations, methods being investigated for standardizing, or in any case, extracting cosmological parameters information from gamma ray burst. And I will focus on the correlation between the spectral peak energy, EP, and the total radiated energy, isotropic equivalent radiated energy, EISO, which is called Amati correlation. I will show why in a while. As most of you, the expert of gamma ray burst, will know very well, as you can see on the left, the typical new spectrum, so the bottom panel of the figure on the left shows typically a peak. So on the average, the typical time integrated spectrum, we know gamma ray burst prompt emission shows a strong spectral variability, but the typical spectrum of the time integrated spectrum has also, in the good fraction of the time resolved spectra, the spectrum is dominated by the so-called, this is smoothly broken power law continuum, which in terms of nu f nu becomes a peaked spectrum, and the photon energy at which there is this peak is called spectral peak energy, EP. And as we can see on the right, both peak and the total radiated energy, because once we have the redshift, we have the spectrum, we have the fluence, of course we can derive the total radiated energy under isotropic assumption. This is, of course, still a kind of a pain to stick to the isotropic equivalent assumption, but of course there have been many investigations on the jet opening angle of gamma ray burst. There are statistical studies on the possible distribution of jet opening angle that is inferred through several observables, but for a single gamma ray burst, it is still very difficult to assess what is the jet opening angle, and this assessment is very much model dependent. This is why it is more conservative to stick to the isotropic equivalent assumption. So in 2002, Amati et al., so the Beppo-Sachs team with a group of Filippo Frontera and collaborators, we investigated the spectral energy properties of the first small sample of gamma ray burst with measured redshift, and we found evidence of this correlation between spectral peak energy and total radiated energy. That was confirmed by later measurements, for instance, by Swift, and all the other satellites, 82, first of all, that came in the years. And this is the status of the peak isocorrelation for long gamma ray burst. There are now almost 500 gamma ray bursts with measured redshift. And of course, for only a fraction of them, there is a good enough spectral measurement to allow him to determine the spectral peak energy. And for this, we can confirm, many works confirm this correlation. Of course, for classical long gamma ray bursts, as I will mention later, there are some exceptions. Short gamma ray bursts do not follow. There are some very investigated outliers that can be explained through different effects. The properties of this correlation are that it is a power law correlation in terms of logarithmic, so it's log spectral peak energy log EI, so it becomes, of course, a linear correlation with a slope of more or less 0.5. And this characterized by a dispersion, so of the points around the best fit, which is significantly in excess with the expected fluctuation due to Bosonian, simply so statistical fluctuations. So it is characterized also by an intrinsic dispersion, which is a very important parameter, which is telling, of course, us something about the jet opening angle distribution and possibly the emission physics. So there are a lot of works investigating, discussing, debating how much selection effects, instrumental effects may, of course, affect this kind of correlation, as for all other correlation in astrophysics. There are several evidences supporting its reliability, that it is not so strongly, or that it is marginally affected by instrumental effects. One is the fact that if we consider measurement from very different instruments, as listed here, that have very different sensitivity as a function of energies, they operate in different energy bands. After all, they provide the same correlation. This correlation also doesn't show significant evidence of evolution with redshift. So if one takes the full sample and divides it into bins of redshift, and for each range of redshift, as done here, computes the correlation, it does not find any evidence of variation of the parameters of the correlation with redshift. And this is consistent with the fact that in general, there is no significant evidence of evolution of any properties of the prompt emission of gamma ray burst with redshift. And it is also well known that if instead of the radiated energy, we use the peak luminosity, so we have a gamma ray burst, the brightness of the gamma ray burst can be characterized by this total fluence, which becomes radiated energy in the cosmological rest frame, or the peak flux, which becomes the peak luminosity. They are an indicator of how bright a gamma ray burst is. If instead of using EIs, we use the peak luminosity, we obtain the same correlation. This is not surprising. Peak luminosity and total radiated energy are very strongly correlated. Of course, there are different quantities, and why they correlate in the same way with the peak energy. Of course, there are many explanations. One may also be that you can use the peak luminosity as a proxy of the total radiated energy, because if you, for a gamma ray burst is weak or is distant, or your detector is not sensitive enough, you will detect only the brightest part of the gamma ray burst. So of course you will miss part fraction of the fluence. You may underestimate the isotopic energy. Instead, the peak you always detect. There are, of course, drawbacks in using the peak luminosity. You have to assess, assume a given time scale, a given energy band. So the light curve peak at different time in different energy ranges and so on. So, and finally, if you do a time resolved analysis, so if you take as here gamma ray burst, light curve, you divide it into several intervals based on statistical consideration or any other approach you may prefer. You do the spectral analysis for each of the time interval. You compute the spectral peak energy and the average luminosity of each interval. You obtain, as you can see on the left, for most gamma ray burst, for most of the duration of the gamma ray burst, a luminosity or flux versus peak energy relation that is resembles very much the same that we obtain on the total spectrum. And if you have the redshift, you put all of these points here. Each point that you can see in the diagram on the left is a time interval of a single gamma ray burst. So each diagram here is a gamma ray burst, where before each point was a different gamma ray burst. And if you put all of these points on the right all together, if you have the redshift, you can see that overall they follow the same correlation. So this is also further evidence that there is a main emission mechanism at work in the measure of the fraction of the gamma ray burst for most or important fraction of the time during the gamma ray burst that produces this correlation. Of course, this correlation has been investigated so much for its implication on the physics of the spectral peak energy. There was a very nice work, by the way, there have been many works on this, a nice review by Zhang and others already in 2002, describing the meaning and the role of the spectral peak energy in several scenarios for the prompt emission of gamma ray burst, internal shock, innermost scenarios, thermal emission, and so on, with different flavor also of the jet itself. And the existence and property of this correlation allow to constrain the parameters in these scenarios. Of course, this work has also been done, of course, by the ICRANET gamma ray burst team since many years ago. This is one example from 2008, in which they could reproduce for some assumptions from some cases the correlation for long gamma ray burst. And as I mentioned before, different classes of gamma ray burst tend to populate differently the PK isoplane, with short gamma ray burst direct point V as being outside, possibly following their own correlation, especially if you use the peak luminosity instead of isotropic energy. X-ray flashes, so the light blue on the bottom left points, extend the PK isocorrelation, whereas there are some points, historically, the famous gamma ray burst 98 or 425, the so-called underluminous gamma ray burst, which do not follow the correlation. So this is the use of the PK isoplane for identifying and understanding the nature of and the progenitors and the central engine of different classes of gamma ray burst. This is again been investigated also by the ICRANET team. This is from Ruffini et al. 2016, where you can see the region, how different classes of gamma ray burst and the progenitor of gamma ray burst populate the PK isoplane. And of course, in addition to the emission physics, this correlation is also including information on the jet opening angle, as I already mentioned, of course, the viewing angle, the jet structure. So depending on if you assume a uniform jet or a structured jet, different viewing angle distribution, you can, as you can see in the drawings on the bottom, different populations of the PK isoplane. And as I mentioned before, viewing effects have also been invoked for explaining the existence of underluminous gamma ray bursts like 98 or 425 or 0312 or 3. There are other possible explanations, these outliers of the PK isocorrelation, which are still long gamma ray bursts, but with some peculiar characteristics, not only being outlier of the correlation, but on their own, very underluminous, with some peculiar properties, and their properties may be explained by the viewing angle effects, which may be are the same effects that have been invoked to explain the peculiar properties of the short gamma ray burst 1708, 17A, which was detected together with the gravitational wave signal from LIGO Virgo in 2017. So same approach. So now let me turn to the use of this correlation for standardizing, let's say, gamma ray burst and extracting information on cosmological parameter. Of course, we have a correlation between the spectral peak energy, which is a thing that we measure. We can reconstruct the intrinsic, so cosmological as frame spectral peak energy, simply scaling by 1 plus that. Of course, we have the fluence, the spectrum, EISO, which is instead depending on the cosmological model, of course, through the luminosity distance. And of course, we could use, in principle, use this correlation to derive cosmological parameters, because we have an observable, which is cosmologically independent, linked to the quantity, radiated energy or luminosity, which of course depends on the cosmology. Here, the drawback, of course, is that differently from type 1a supernovae, which, by the way, we don't have very low redshift gamma ray burst, so to allow a calibration of the correlation in a cosmologically independent way. So to avoid these circularity issues, that we want to use a correlation that was discovered by assuming, of course, a standard cosmology to compute the ISO, we want to use it in turn to measure the cosmological parameters. This can be avoided with an approach that has also been studied for other probes and also for high redshift type 1a supernovae, or to check the autoconsistency of type 1a supernovae, which is to very simply include the cosmological parameters and the parameters of the correlation and fit them simultaneously. Very simply, the first exercise that one can do is to ask, but what does it happen to the goodness of fit of the correlation if we change the value by assuming a lambda flat lambda CDM scenario, so with only one cosmological parameter as free omega m, if we assume different values of omega m for computing EISO. So we assume omega m at 0, compute EISO for each gamma ray burst, and fit the correlation. Omega m 0.1, omega m 0.2, and so on. No? We grid, we do let's say, or we marginalize over omega m, and what we obtain is that the minus log likelihood as a function of the value of omega m that is assumed to compute EISO has a nice parabolic shape, minimizing right at omega m around 0.3. So very simple, very clear. We included all long gamma ray bursts except for the very few outliers which have peculiarities that justify their exclusion from the sample. We are basing on isotopic equivalence assumption, so we are including all our ignorance on the jet opening angle distribution. Still, we were already in 2008, and nowadays we are even more sensitive to the cosmological parameters, in this case omega n. So this is a very clear result. If we could do this in the 90s, in the 95, for instance, we would have had an indication, at least, that if the universe is flat, as coming from CMB, from expectation of the inflation scenario and so on, we would live in a universe where omega n is significantly lower than 1, is around 0.3, and this implies an accelerated expansion. This is completely independent on other cosmological probes. And of course, through the last study of the likelihood, we can also quantify the value of omega m, as you can see in this table, going from 70 original gamma ray bursts investigated in 2008 to recent sample of 200, more than 200 gamma ray bursts. The accuracy is improving significantly, and is improving more or less with the square root of the size of the sample, which is exactly what you expect if you are not dominated by systematics. We can also release the flat lambda CDM, the flat assumption, so let to vary also omega lambda, and this is what you obtain. This is the purple contour coming from gamma ray burst. As you can see, it's not so it's comparable with what we could obtain with type 1a supernovae or other probes a few years ago. This is a few years ago, but just to see that it is still consistent. It provides a different orientation of the contour in the omega lambda plane, because as I mentioned before, of course, this depends on the redshift distribution of the probe with respect to type 1a supernovae. So, of course, there are also many works. So, again, if this is very interesting, this is deserves a lot of investigation, but this is not, let's say, carried on by only some groups. So there are hundreds of papers published on main journals on the use of the PKIs and other correlation, but especially the PKI correlation for this specific purpose of investigating cosmological parameters. A good fraction of these papers, of these works, actually calibrate gamma memory burst through type 1a supernovae. So if we believe in type 1a supernovae that they're not dominated by systematics, and we believe they result for cosmology, we can take gamma ray bursts that have a ratio level lower than 1.4. We use the luminosity distance derived from type 1a supernovae and reconstruct the correlation, calibrate it, and then use to extend the Hubble diagram, as is shown here. Especially on the bottom, you see the Hubble diagram, so luminosity distance or mode distance module is a function of redshift, as with in blue type 1a supernovae, in red baryonic acoustic oscillation, and in black gamma ray burst. This is very, 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 very nice.
Lorenzo,
So
you have 5 more minutes.
Okay, I just yeah, a couple of slides and concluding. Thank you, See. So again, with a mission like Theseus, which will first of all extend so much our sample of gamma ray burst with redshift, and especially at very high redshift, but in general at all redshift, will also be capable of detecting and characterizing any class of gamma ray burst, not only a redshift, but also short gamma ray burst, X-ray flashes, underluminous gamma ray burst, ultra long gamma ray burst, any class of gamma ray burst, and all the classes of gamma ray burst that are predicted and explained in the scenario that has been developed by the group, by Remo and his group at ICRANET. So this will be really an ideal mission, joining all this possibility of detection with redshift measurement, and also, again, with this capability of measuring the prompt emission spectra and also timing properties in a unprecedentedly wide energy band, from the soft X-rays, which means even below 1 keV, up to 510 MeV. And here I show on the top left the effective area. So you compare the XGs, the monitor of Theseus compared to current measurable detector, you can see the difference. And you can see on the right the extension of the spectral measurements of Theseus with respect to, for instance, the Fermi GPM. And this is what we could do, getting back to measuring cosmological parameter or investigating dark energy evolution with the PKS or peak luminosity correlation in general, or gamma ray burst correlation, you could expect with a huge sample as produced by a machine like Theseus. Like, consider the last line of the table. Very accurate measurement of omega m, but also possible accurate measurement of the parameters of the equation of state, for instance, of dark energy. So I just, of course, again, such a machine will allow also to deeply investigate the physics and do fundamental physics with gamma ray burst. These are, again, studies based on current measurements from the ICRAN GRB group, but with a machine like Theseus, again, this will be done in a much more accurate way. And of course, I would like also to mention the possibility of using gamma ray burst for test of fundamental physics, like testing Lorentz invariance violation, which is very important for assessing classes of quantum gravity models, for instance. And again, a machine like Theseus is very promising under this respect. So this is my conclusion. As I mentioned, just to conclude, the Theseus space concept is an advanced development state because it was studied for 3 years and developed for 3 years by ESA. It's being reproposed to ESA, but also to other agencies. So I invite all of you to go to the papers. There are many papers on the archive, published on the case, science case requirements and the mission profile, or on the website. And thank you very much for your attention.
Bellissimo presentazione. Very nice.
Thank you very much.
Very nice, Lorenzo.
Grazie. Thank you.
And you will see some additional results shortly. And all my best, and be successful in this great mission.
Thank you. Thank you so much, Remo. We will collaborate on this. Yeah.
Okay, thanks.
I also want to share the wishes for success, but I must correct a common mistake which I already referred to in my talk on 2 days ago. 1708-17 and also the 2 other low luminosity gamma ray bursts that you mentioned cannot be under any circumstances, regular GRBs views from the side with a different boost. This is impossible. It is very simple exercise to prove it. It is there are several papers demonstrating it, and I wish that this mistake will not be repeated. These are different objects.
Thank you, Zvi, for pointing this. Of course, I reported explanation in the literature, but of course, I missed to include instead the other explanation. So it's very interesting that so the message is there wanted to be that also the peak isoplane or the peak luminosity plane may be used to identify and understand this peculiar gamma ray burst. I agree. Yes. I agree. I agree with you.
It is a wrong statement that was made in the original Fermi paper reporting on this. Even so, even at that moment, it was clear that this is wrong, and it was pointed out to them. But it was fancier to say it like this and simpler. And it is unfortunate that this wrong statement is propagated in the community as if this is a fact. We are doing science and not fake science. Mm-hmm. Fake news we leave to politicians.
Okay. Okay, thank you, Zvi, for pointing out this very important.
I ask a related question because we were discussing yesterday this point about this dichotomy between the let's say normal higher energy GRBs and the lower energy GRBs. So do you think that this wider band of the seals can maybe fill the gap? There is a possibility. Do you think that there is a observational bias or it's a real dichotomy?
So sorry, to what bias you were referring? Sorry, I didn't catch.
No, the dichotomy between high energy and low energy and the luminous GRBs.
Okay, yes. Well, yes, I think that this was the main message. Mission light Theseus or even a GRB monitor like the one on Theseus, that is an Italian developed instrument, would allow for sure to expand a lot with the current capabilities of current or near future GRB detectors. So it is the ideal experiment to actually allow us to fully understand and discriminate between different classes of gamma ray burst and to get insight on the nature. Because as I mentioned, such a monitor will combine a huge energy band, especially if flanked by the soft X-ray monitor, so which will cover in total energy band from 0.3 keV up to 10 MeV, with an effective area from 1 keV to 10 MeV. That is much larger, for instance, than the GBM. So if you compare such an instrument with the GBM, for instance, well, it's very, you can have a look to this drawing on the top left, where you compare the effective area, which means larger the effective area is, better is the sensitivity, gives you a comparison. So we will fill the gap between 10 keV, below, sorry, 10 keV, which is affecting currently all currently previously flown gamma ray burst detector, and this key for detecting the bulk of the population of X-ray flashes under luminous gamma ray burst and understanding them. And this will also be joined with very good spectral accuracy and also timing accuracy. So I'm quite sure that this will provide a substantial progress.
Thank you very much. We are short of time, so we will stop here and thank you again.
Thank you, Zvi.
It's a very fascinating talk.
Thank you.
And we will continue with the program. You are the next here. And Jorge Rueda is the next speaker, which will be given on Zoom, but also in live here in the office.
Okay, thank you very much. So I will share my screen now. Okay, here we are. I have to put in presentation. Okay. Somewhere. So I start. Okay. So this is thank you. It will be a pleasure to continue. I made a talk on made a presentation on Monday on a different part. I stopped on the part on the related to compact star physics, neutron star and white dwarfs, and now I move to case of GRBs. I put now here somehow different title with respect to the one the abstract. The same. My original title was the latest of developments. As an update of on our model, binary driven Hypernova model for gamma ray bars from GRBs. But well, it's essentially the same. I just would like to highlight here that I would specialize on the role of each of these the binary components of this system. So just to start with this one of the when I start to enter into the topic of GRBs, at the beginning, there was this a picture of the was going on in the GRB group at Sapienza and Ikram on the expansion of the electron, studying the expansion and the creation of the electron-positron plasma that eventually self-expand and reach transparency, and transparency explain the gamma rays of the GRB. Well, this is still a part of the model of that we are studying and we are proposing, but in a somehow different way. It's now a much complex, a more complex picture, and this is what I would like to share with you today. So then this there was that original idea that you see at the upper right figure, that the scheme of the induced gravitational collapse proposal in 2006 actually was a bit before, maybe it was 2002 paper, but it was an opposite process than the one we are considering right now, because there was the association that with supernovae, between long GRBs and supernovae 1C. And so they were considering a picture in which the GRB was triggering a supernova event in a binary system. Then actually what we made was to make a different idea. Maybe it was more natural that there was a supernova will trigger a GRB process, something related with gravitational collapse. And this was the our paper in 2012 when about the induced gravitational collapse. So we are considering here star in a binary system with a neutron star companion. That was the original idea. Then this star undergoes a supernova explosion, and there is an accretion process that you can see here onto the neutron star companion. And this eventually is if the parameters of the binary are the right ones, this neutron accretion process can be strong enough, massive enough to bring the companion to the critical mass, and then this neutron star will collapse into a black hole. And when it creates the black hole, it could be then the possibility of triggering all the process that there was studied before in our group, of the positron perihelion, self-expansion, and all this. So that was the idea was to how to create the black hole and to have the supernova at the same time. So that was the idea of the induced gravitational collapse. This is why this picture. This is a Soroush school of the PhD program that actually with the Erasmus Mundus joint doctorate program. You see next to Remo, you see Chris Fryer. Here, here is Chris. Okay, I don't know where I am. I'm here. Okay, and Chris Fryer at the time came to our school to show. He told us, I'm starting to study your proposal of 2012, and I wanted to show that it couldn't work. So I wanted to show it couldn't work. Then he came to our school. He said, I will show you how I fail. I failed in showing that. So actually he started to perform some simulations of the accretion process of the supernova explosion with the companion. And he started to see that indeed this could happen. I mean, the accretion could be massive enough to bring the neutron star to the gravitational collapse. And there's some astrophysically viable conditions. So this was Chris. Then this was our work, our first work with Chris, the first numerical simulation. It was the first time that we used the name binary-driven hypernova, by the way. This was in 2014. So we simulated the supernova. You see, this is a scheme, but this is the real. This is the result of the simulation. This was just scheme. Taking into account what was the ongoing physics of hypercritical accretion onto the neutron star, so physics of neutrinos, or hydrodynamics stuff near the neutron star surface. So so we showed that it could actually happen. The accretion rate could be up to of the order, let's say, to give a number, 10⁻² solar masses per second. And so eventually the neutron star can collapse and form a black hole.
Sorry, because it's fast for me. So you have a neutron star with a big accretion disk, and the neutron star collapses as a black hole, and at the same time there is a supernova. The
supernova was before. So you have the star, and you have the neutron star companion. There's a binary. The star explodes, then this matter that is being expelled makes trigger the accretion process onto the companion. And then it collapses and form a black hole.
What Nathalie is asking is whether there is a mass transfer between the star and the neutron star before the collapse also. If the star is close enough to the neutron star, there should be
these are conditions that we avoid. So we choose parameters for the system exactly to which are the parameters that in which Roche law overflow doesn't happen before.
Okay, so there is no accretion disk, and the stars are far enough that there is no accretion, but sufficiently close by that there will be
accretion by supernova.
Amount of the supernova falling onto.
Yes, that's exactly.
What's the time scale between them? Because the accretion disk is
these are orbital periods have to be of the order of minutes.
What is the separation?
Longer than 5 minutes, because if you go too close, then will be Roche law overflow, and this will not happen.
Yes, but then when you have the supernovae, then there is mass ejection, which forms a brand new an accretion disk around, and then but this overflow must be very significant, because very soon you must have enough matter.
Yes, you see, the time scales are short. Actually, time scales are short. Everything happens in just a few minutes. Everything happens. It's a question of minutes.
Typically, the binary is a period of several hours.
Yes. Yes.
So if you have a period of several hours, you already have Roche law overflow.
Oh yes, but this is but this is a later stage of evolution, and this is made for carbon oxygen stars. This is not. It's not for big. It's not for big stars. Yeah, exactly. We have strict envelope. So this was the situation at the time. Then we these are we use at most 8 solar masses at most. In our we have simulations from 4 to 8 solar masses of the carbon oxygen star. Not more than that. Well, it was including angular momentum transfer to the star. This was our first simulation in 2D, and also showing this is the evolutionary path of the neutron star while accreting, accounting also for the angular momentum of the neutron star, and accounting for general relativistic effects. This was 2015. Again, this was Chris Fryer in Pescara in 2016, and he was signing the wall on in the underground of Pescara headquarters. Why this picture? Because in this 2016, we're making our first simulation that I will show in a moment. But this was special because of that, because we start to think about how to do this in a high resolution in Los Alamos. But we started to discuss also the variety of the GRB subclasses, because we were discussing just right now, you have different masses, possible masses for the star, exploding star, different parameters for their orbital period, maybe different parameters for the mass of the neutron star companion, or this initial angular momentum. You have parameters to play with in this system. Of course, it means that this system could have different fates. If you have different fates, maybe you have different observables. And so this will lead to a variety of observational features of GRBs. So at the time, this was 2015, we just were thinking about two possible families. So there were the systems in which you collapse, the neutron star collapses, and the system in which this neutron star it doesn't collapse and just stays just as a massive neutron star. This is actually a main, let's say, still a main two family separation that we think this is the main two fates of this system that we actually today we call it binary driven hypernova of type 1, in which you form the black hole, and type 2 in which you don't. Well, we show also that if the binary is compact enough, then it could even resist the explosion without getting disrupted by the explosion. So this was another result. So eventually in the most compact, you can form neutron star black hole binaries that eventually they could form short GRBs in the future when the merger occurs. Well, the picture was evolving in the sense that we start also to continue to study what would be the different classes of this GRB, this classification of GRB. And this was the picture that Lorenzo showed before. The possibilities here, we study both the long and the short GRBs, but today I'm focusing on the long, that were these.
Sorry, I missed something, because for the moment you are not explaining how the gamma reverse are. For the first, I missed something. You talked about this supernovae and the star with the core or not, and the gamma reverse.
No, because the gamma reverse would be, well, is that GRBs are different. They have different observables. Okay, different.
So now you switch topics to describe the various classes of gamma reverse, and then you will explain how this model will.
Yes, because that you see this process. You have the explosion, you have accretion, then you have collapse, yes. And then you have a new system eventually, and you have the black hole, yes. and you have still the matter around expanding. Yes. You have also still the neutron star that formed from the supernova explosion, and so all these create observables in the GRB itself. So
why it comes from where?
So GRB is all.
You're not talking about how.
So GRB is when we call this a GRB from the observational point of view. This GRB has maybe a precursor in X-rays.
I just wanted to see the logic of the whole.
Okay.
So now you're talking about GRBs in general, and then you will go back to your own.
Yeah, so GRB is all nice in the literature. GRB is in the entire process. So, but it has maybe a precursor in the X-rays. Then you have the gamma. No, but this is important. It's the prompt gamma rays. Then you have the prompt gamma rays. Then you have the afterglow in the X-rays, observing the X-rays in the optical, in the radio. Then after you have also the optical emission from the supernova. So you have a difference, but we call everything this is the GRB. But when we call about this, we separate. In fact, what is the responsible for each of these pieces of the GRB in our system? Okay, so I will come to this. Okay, so we have this separation between the two, and eventually you have also a relation between long and short, because you could form binaries, compact star binaries from this. So well, this with the simulations, but I will jump to the to Natalie question actually. Here is I will speak a little bit about that. So so what's the idea that you have in the black hole, and I will come into that. It was not my topic. I think Rahim Moradi will speak about that later, or he spoke on Monday. That somehow you have to form this electron-positron plasma that expands and reach some high Lorentz factor to reach transparency at some point to explain the prompt gamma ray emission of the GRB. So this is one of the main issues of the GRB. So here what we have then is that this in the formation of the black hole, you had at the beginning the neutron star with the magnetic field. So eventually you have the black hole with the magnetic field. The black hole rotating with the magnetic field induces the electric field.
This is the stuff that I told.
Yes, you have this electric field. This electric field, if it is overcritical, create the pairs that will be the seat of this electron-positron plasma. This electron-positron plasma then has to expand in this. You have to expand in the material around. The material around is not spherically symmetric anymore because of the action of the binary, the accretion of this, and this comes out from the simulation. So, and this plasma, this electron-positron plasma starts to expand into this matter along different directions. It finds a different amount of baryonic matter. This is what you see here. This is the amount of the baryonic matter as a function of the angle, starting from this would be 0 direction, and then you go into this direction and it finds different amount of matter. Why this is important? Because it means that this electron-positron plasma reaches transparency at different times and reaches transparency with different Lorentz factor along different directions. So when the plasma finds a low Lorentz factor, a low baryon load, baryon it carries a low fraction of baryons, then it reaches high Lorentz factor, and this happens along. This happens along this region. See, along this is the region of low density, and then this is the region in which that's the region in which you can see a prompt gamma ray emission from the GRB. Instead, there are other directions around where the plasma finds a higher density, and in that region, eventually, it can reach only a gamma factor of the order of 3, between 3 and 5, let's say. And in that region, eventually, you can see only possible, this is what the simulation of this paper, a flare. Maybe this is just a flaring activity that sometimes you see at the beginning of the after.
Why is it that one region is baryon depleting and another one?
Yes.
It comes from where?
Because of the accretion process.
Because of the presence of the other stuff.
Yes. So that's modified completely the morphology of the supernova material. You can see even better here. This is a high resolution simulation where you see even better how this material is depleted around the accretion region. So these are actually the latest simulation that we have from this system. Well, this was you can see also here how this you see this like a Chinese cookie morphology due to the accretion. And these are simulations of the different accretion rate that Laura showed already. So I will not stop here and go ahead. So, but this is let's see a global picture of what is the model. So the transient of the GRB occurs therefore at the second supernova explosion of this binary system. So Professor Piran was speaking before about what's here, about this the X-ray binaries, but then eventually, if you have then possibility of common envelope phases and all this to strip the outer envelope and form a carbon-oxygen star, a small one. And then in the second supernova explosion, and here this process will occur at the process of the binary-driven hypernova. And so you have all these. The role for the system is, I mentioned, you form the black hole that can create the electron-positron plasma. It will explain the gamma rays, the prompt gamma ray emission. But not only. The black hole will eventually, this mechanism will be also responsible for the high energy emission in the GeV region. Not because of the electron-positron plasma, because eventually this phase, when I'm here, this phase, this quantum electrodynamic process, because this is vacuum polarization that create the plasma, finished, and then you are end just with the synchrotron emission. If you have still some material, some electrons around, these are accelerated by the magnetic field, by the electric field, and they produce synchrotron radiation. That typical energies of this radiation, it goes in the GeV regime, and that is would be the explanation.
This is coming from what distance from the black hole?
Oh, that would be close to the black hole. That is.
Then again, you get a compactness problem, and they will not get up.
No.
They will produce electron. The high energy gamma rays will annihilate with low energy radiation, produce electron-positron pairs once more, and you will get an optically fixed system, and you will not get the GeV emission.
Yes, that would be, if the emission would be isotropic, this would be,
It does not depend on isotropic or not. It depends on the.
Well, you need to annihilate the photons. You need to annihilate photons.
You have
so you need all cones of radiation pointing everywhere, but this is not the case in this system.
So the energy excess between the GeV photon and the low energy photon is sufficient that even if there is small angle between them, that will be sufficient to correlate. Unless you somehow miraculously align all the radiation, that it will be completely parallel to each other. This is impossible.
No, it's not impossible. Why you say that?
This is fine tuning, but it's not impossible. It's fine.
No, it's not fine tuning. It's not fine tuning.
I don't know.
It's not fine tuning because no. But these points are important. It's not that is completely fine tuning. I mean, these are astrophysical conditions to create a process. It's not that you are fine tuning. You have the picture. You have the magnetic field, and you have the electrons accelerating. In this region, this happens in a very short length scale. Then you have the cones of the radiation are extremely beam radiation, and these make the probability of the interaction to decrease.
Why is it so big?
Because the electrons are accelerated up to gamma 10 to the 5.
But then the synchrotron radiation is not along the magnetic field, it's in this direction, so it goes in all directions.
No, you have the cone of the beam for the observer at infinity. The observer, the radiation is beam toward the motion of the electron.
Is there a barrier?
No, but this is not you've got the synchrotron radiation, but this actually they are accelerated by the electric field. I mean, the motion is accelerated by the electric field up to gamma 10 to the 5 along the attached to the magnetic field line. But the magnetic field line in this system, the magnetic field line across the backbone, they are all parallel in that region. They are all parallel. I mean, it's not like in the that.
If they are all parallel and the electrons move along the magnetic field, then there is no synchrotron radiation. Synchrotron radiation arises when the electrons go around the magnetic field.
Yes, I know.
So if you have 10 to the 5, gamma 10 to the 5 electron going along the magnetic field, this does not produce synchrotron radiation.
No, this is more the linear acceleration if you want to call it, or curvature acceleration, or maybe small curvature or whatever.
Oh, if there is curvature acceleration, then the magnetic field is not parallel. And if the magnetic field is not parallel, then there will be some deviation in directions, and then you will have the problem that I mentioned before.
I agree with you.
You cannot ignore. Okay.
No, I agree with you that you eventually
some
have this problem.
basic physics issue which are wrong. I'm very sorry.
Well, I'm very sorry too. I mean that, yeah, if you like, we can look at the numbers. I know what you are saying. That you have to look and compare and compute the interaction between the photons, the radiation, and to account the cross section of photon interaction.
This is computed. It's not in isolation. There is a lot of soft photons coming from other regions. So even if you have high energy photons, which are all in one direction, but you will have sea of external photons. And these external photons will interact with these high energy photons. If you're talking about distances of 10 to the 6 centimeters, this is just too small. And the cross sections are, and the densities are so large that this will simply produce flares, and you're going back to the situation of electron-positron cloud that we discussed.
Yes, but I know why you see that you have these soft photons. I mean, for these energies, you would need soft photons with regime, maybe 10 electron volts to have a high cross section.
And the system is not quiet. You have all this matter moving around.
Yes,
but let's finish that.
No, but this is
my naive questions that perhaps may be related. Because you have this accretion disk, and now you have this region close to the black hole with the magnetic field, and this is where this accretion takes place. And my question was, how far is it from all this matter, this accreting matter, which is still around?
You mean the electron-positron plasma when get transparency?
Because your model, as far as I understood, is that you are so suddenly arriving at this full neutron star. You have a lot of accretion matter coming from the supernova, which just happened. And then this accreting matter falls on the neutron star because it turns it into black hole.
Yes.
And then you will have this magnetic field and the rest of it in your model. But there is still some accreting matter all around. So this plasma, electron plasma, which is formed by this magnetic field, in fact, there is all this incoming matter on top of it.
Yes,
And there are interactions between this matter that you produce and this accretion disk.
No, the matter, well, we don't have exact an accretion disk, let's say. There is some circularization of matter. That would happen at close radii, 10 to the 7, 10 to the 9 centimeters. But the electron-positron plasma, when it forms in self-expands and then it goes in the low density region, I made the simulation of this, taking into account the interaction with the matter. It goes and get transparency at 10 to the 13, 10 to the 14 centimeters, something like that. So well beyond that region. So the problem here, and actually we acknowledge this into one of the latest papers about the problem of these GeV photons with the low energy photon bath, possibly to account for this photon interaction that Professor Pirani mentioned. to tell you what we mentioned here is that we expect, because we didn't compute yet, because I think it's not simple calculation and it's not simple as to say it will create a lot of pairs. I don't think, in my opinion, but my personal opinion is not possible to say that at the present without making a detailed calculation. For the specific conditions of these systems, I don't think it's as simple as that. That's assuming like you can assume that the cross section is of the order of Thomson cross section. So this is my guess here. Well, so it was the role of the this is the role of the black hole, the interaction of the black hole with the magnetic field, the electric field, acceleration. These are the analysis of the GeV emission. I will jump here. Then I come to the possible role of the role of the new neutron star, the newborn neutron star formed at the center of the supernova. So you have ongoing how long I can speak now. I think I don't know how much time.
I started a bit late, so
I don't remember.
Getting to the coffee.
I didn't get. Okay, I will try to just.
Squeeze the coffee.
Yeah, no. I will squeeze a bit my presentation just to mention the role of the. So we mentioned the role of the black hole. We mentioned the role of the neutron star form at the center of the supernova. So this is just this is a recent calculation. Actually, we're focusing on the first instance. In the first instance, you have the accretion, and so it's a possible role on the possible precursor. Precursor is a mission that you could observe, that can observe. You observe sometime before the prompt gamma rays. And so this could be just a signature of the early accretion ongoing, not only on the neutron star companion, but also on the neutron star at the center because of fallback. And so this is this simulation of how this is the energy gain actually of these of both neutron star companion and the newborn neutron star at the center of the supernova because of the accretion process. So the newborn neutron star is the black, and these are different. These are different possibilities. This is dependent on the initial angular momentum of the neutron star companion. You could have different possibilities. So this is due to accretion. So are the two ongoing accretion process that make eventually the stars to gain a lot of angular momentum and increase this energy that you can be emitted in these early stages. And so you can get something up to 10 to the 50 or 10 to the 51 air per second that you can emit. So I think that this could be we could see the sign of this early emission in the precursor. So this is a possible role of the new neutron star. This I will jump. We will speak about this. This is just the model of what we call the inner engine. So it's the black hole with the magnetic field producing the electric field, and that causes first the electron-positron pair plasma for the prompt gamma rays, but also the emission of the GeV emission. So
what is the strength of the magnetic field that you need?
For the GeV?
So in your model, what is the strength of the magnetic field? You have a rotating black hole.
Yes.
That you immerse in a uniform magnetic field. And a very simple question. What is the...
You need 10 to the 14.
10 to the 14?
Yes, because otherwise you cannot create the pairs at the beginning.
Over what volume? Over what kind of volume?
Let's say 10 to the 7, 10 to the 7 centimeters.
And what is the origin of the magnetic field?
The one is left from the neutron star before.
Or the original from the neutron star? So you need so the original neutron star has to be a magnet.
It has to be magnet, strongly magnetized. Instead, for the GeV part, actually, and this is also important. Actually, what could happen is that that's supposed to be a screening of the magnetic field. Actually, for the part of the GeV, for the part of to explain the GeV, you need only 10 to the 11 Gauss. Actually, to explain that, not 10 to the 14.
Produce your gamma reverse, then the strength of the magnetic field must decrease, I guess.
Yeah, you need 10 to the 14 because otherwise the electric field that you induce is not supercritical.
Okay, so I understand.
Yeah.
But once you have produced your electron-positron pairs, I guess the back reaction makes the Exactly. Well, we made some simulations of this. It's not easy, and we are starting. We made some first model of that, and in fact we see the screening of magnetic field by the pairs. We see that. I don't have here the picture of the simulation, but we just published that a few months ago about the first simulation of that back reaction. But there's a back reaction force that you write.
No, but this is not this problem. This was just the motion of the particles and the GE emission, but we already touched this problem. So I will jump to the other part. So we have a possible role of this new neutron star, this newborn neutron star, also in the synchrotron afterglow. If it is emitted by you have the supernova expanding, but being energized by the emission of by the power of the neutron star rotational energy, which is big, and that eventually can explain the X-ray optical and radio afterglow. This is an example of 18, the GRB 180720b. You have this optical emission in blue, this radio emission in gray, and you have the red. They are the X-rays. And actually here you have a synchrotron. This is a synchrotron model of this expansion with this energetic power from behind. And you see actually the synchrotron, you can explain actually this X-ray, but the optical and the radio, yes. This is because synchrotron radiation, the radiation frequency is shifted from hard to soft during the evolution, and so eventually these X-rays, this curve here will be from the direct observation of pulsar emission of this, let's say, magnetar at the center. So this would be also the role of the new neutron star at the center of the supernova. Well, this was, I think we are jumping to the last slide. This is something about the gravitational wave emission from the GRBs. This was some results from 2018, where we were estimating the possible gravitational wave emission from all these classes of GRBs. But not from the original one, because in this process of collapse, and the gravitational waves are of course negligible, but from the possible binaries that are left, and from the merger of compact star binaries, then you can using the observed rates of GRBs, you can extract some numbers from the possible detection of these mergers. But this is a recent problem that we highlight. There is maybe the possibility to have a strong gravitational wave emission from the new neutron star in the early evolution, because as I mentioned before, this late X-ray emission seems to fit with the rotational energy as being paid by the rotational energy of the new neutron star. So what we assumed, what we thought was, so let's see what happened if we extrapolate back this power law observed emission. So like we are always paying the energy with this rotational energy. So what happened is that this power law matches with some emission here at in the early emission of the GRB that we call the new neutron star rise. So this energy here, this amount of luminosity, can be explained by the rotational energy of a highly rotating neutron star. And actually, we look at, if you model this new neutron star as a Maclaurin asteroid, and you derive the parameters of the eccentricity, for the eccentricity, mass, and radius, you end up with a number which is close to the bifurcation point with the Jacobi sequence. So we were thinking that maybe during the accretion process at the beginning, if you allow for triaxiality in the system, this star at the beginning will have some triaxial configuration, and then you have to evolve, of course, from triaxial from an ellipsoid to a spheroid, emitting a large amount of gravitational waves. And this from our calculation, this should be a signal detectable up to 100 megaparsec. For the current interferometers. So this is a possibility to test the presence of this evolution of the initial neutron star. So there is much to be studied, of course, in the short and medium term, also in the long term. There are many questions, many still things to be studied, calculated. So I put here some of them. First two are from a discussion that we had with Zvi yesterday. So I put the first two questions. The origin of spectrum. So emission as quasi-thermal or deformed thermal when you take into account the convolution of taking into account the Lorentz factor as function of the angle. But still, you see there is a non-thermal component in the prompt, okay, that we have to model. So we have to model that. What is the origin of the dichotomy? Yes, this is my last slide.
But if you go over all the things, it will be 10 minutes. So, and we have 5 minutes for the coffee break because the next speaker told me that he cannot wait.
Okay, that's okay. So this
about the risk, what is the most difficult one to solve? Just pick the one which is the most worrying for your moment.
No, I can tell you what I would like most to do.
Yes.
And are the last point that are from the physics of this system.
And for sure.
No. No. How to use from this modeling and comparing with observations, how to extract information to constrain the physics of neutron stars. This is what I like most. What I try to do. So comparing observed rates and observed rates of long GRBs and energetic GRBs to extract information on the critical mass on possible phase transitions in the neutron star. This is what I would like to do most at this moment.
Thank you. We have 5 minutes now for questions here. So are there any questions from the audience? From the Zoom?
Let's see if there is any. No, I see.
No. Cosa fate? No. Interrompete per un momento e poi ritorni.
So we will have some short coffee break.
We will have a very short coffee break and we'll meet at 5 minutes. 11:15.
Okay.
Okay, so welcome to the second part of the session. Our next is the University. Pleasure to invite him here, very good friend, and we'll hear about what observation tells us about gamma ray bursts and supernova. Please.
Thank you very much. So first, I would like to thank you for inviting me. I do not have a long-standing past familiarity with Remo, so I was a bit surprised and very delighted to be invited. So I do not have any stories. So all I can say is congratulations for your Remo for your 80th birthday.
Thank you very much, and thank you for accepting. We have studied many of your papers, and we are very happy to see you here. Thanks.
Thank you. So actually in my talk, I will have two different topics. In the first one, I would like to answer a question which I don't know how many of you ever asked, whether the supernovae, which is associated with long GRBs, can be driven by the jet itself. So as Tzvi was showing earlier during the conference, as the jet is propagating in the stellar envelope, it is depositing a lot of energy into the envelope. In principle, it's known for a long time. I think the first paper was by David Elazzati, showing that this energy can actually explode the star. It's depositing enough energy to unbind the envelope. And later on, there were several papers claiming that this energy can actually produce a supernova, which is rather similar to the broadline 1C supernovae that we see associated with GRBs. And of course, in astrophysics, we always prefer to be economical. And if we can have two birds with one shot, it's always better. So the first question will be whether we can have only the jet and that's it, and produce a supernovae. And if not, it will tell us something about what are the expectations, what are the needs from the energy source or energy sources that are at work in long GRBs. The second part of my talk will be also relating to constraints on the engine, but different one. So I'm going to ask a different question. I'm going to ask, what do we know about the time scales, the long-term time scales of the engine? So the expectation is that the duration of the engine should be such that it shut off not very quickly. So, for example, if we're talking about slowing down of a magnetar, there is a continuous injection of energy and then a decay as a power law. And I will try to ask what the observation tells us. Do we see this decay phase of the engine or not? So it's almost two different questions. So the first one, can a GRB jet drive a supernovae? It's based on a paper written by my student Moshe Eisenberg. I will first give a bit of an overview. I apologize if I repeat some of the stuff that Tzvi said on his talk. If you already know that, so I will just refresh your memory. So we're talking about a jet propagating, in this case, in a star. And of course, there's the interaction between the jet and the star, and this interaction produces what we call a head. There is a forward shock, which is propagating into the star, and a reverse shock, which is propagating into the jet. And the pressure in this head is very, very high. So the material is escaping sideways, producing what we call a cocoon. So as the jet propagates, at every given time, it spills material to the sideways, engulfing the jet itself and producing a high pressurized bubble. Now, if the head is non-relativistic, we already have shown in the past that the pressure of the jet should be, the pressure of the cocoon, sorry, should be high enough to actually collimate the jet. And above the collimation, the jet is propagating in a cylindrical way until it's breaking out of the star and spreading sideways. Here you can see a comparison between the theory which was developed by Omer Bromberg, including Tzvi, Ram, Sari, and me about 10 years ago. And on the left, you see simulations that actually check and calibrate this model. I would like to draw your attention to one property of the cocoon. So the cocoon is composed out of two different types of material. There is a material coming from the jet, which is going into the head and into the cocoon. And there is a material coming from the surrounding medium, in this case, the stellar envelope, going into the head and into the jet, or just shocked by the shock as a high pressure in the cocoon drives a shock into the stellar medium. Now, these two regions are not well mixed. So we have a very hot and dilute region, which we call the inner cocoon, and a much denser and colder region that we call the outer cocoon. If we look at the energy per baryon here, you can see that actually the energy per baryon, yes, this is on the left. You can see that the outer cocoon, the velocity is about 0.1 c or slightly lower, 0.01 c. And in the inner cocoon, the material is mildly relativistic, the temperature is mildly relativistic. After the jet breaks out and the cocoon is breaking with it, the material in the inner cocoon is peeling out and accelerating to a Lorentz factor of 2 or 3. And the material in the outer cocoon is expanding and spreading out with a velocity of about 0.1 c. So let's look at the simulation. And in this simulation, you will see a jet. The jet is successful. And actually, I would care about what happens to the cocoon and what happens to the shock, which is driven into the jet. So you can see that the jet is breaking out. And just at the point of breakout, you can see here the inner cocoon. This is basically like energy per baryon. This is the final Lorentz factor that each fluid element is going to accelerate to, or for velocity, some of the material non-relativistic. You can see here's the inner cocoon with velocities which is mildly relativistic. You can see here the outer cocoon, which is sub-relativistic. And you will see first that the inner cocoon is expanding in all directions. And there is a lot of energy. By the way, the energy in the inner cocoon and the outer cocoon is comparable. So we'll have about half of the energy escaping with a Lorentz factor of 2 or 3, and the rest is still remaining inside the star, driving a shock into the envelope. Okay, so now the very fast material already escaped. Now the slower material, which is coming from inner part of the inner cocoon. The inner cocoon also has some stratification in the energy per baryon, is escaping. So now you see material which is Lorentz factor of say with a beta of about 0.5 is escaping. And you can see that the shock here, which is going into the star, it's starting it's propagating to consume the entire stellar envelope, producing material with velocity that is going down. So look at the material which is going out, and you will see that we go from yellow to green to blue. Let's continue. Oh. Now it's becoming slower. You can see that the shock here is decelerating, producing slower and slower material. And by the time that the entire star is consumed, we have a material that was escaping from the star. This is nothing to do with the jet. The jet is continue to go out and producing ultra-relativistic outflow, which is later producing the GRB. We are now talking only about what happens with the stellar material in the cocoon. And we have actually an outflow with a very, very wide range of velocity. So it's going all the way from the fastest material coming from the inner cocoon, which will go at a velocity of Lorentz factor of 2 or 3, out to the material which is shocked near the end from the stellar envelope, which is actually escaping at a velocity which is comparable to the square root of the energy deposited into the envelope, which is the cocoon energy roughly, and the mass of the star. So what we did was following, this one. So what we did was following the stellar material as it expanding until it reaches the homologous phase. And then we asked how much energy either per logarithmic scale of velocity. So let's start with the blue curve here. This is a spherical explosion. This is a spherical explosion, and as expected, the center of the typical velocity is the square root of the energy of the explosion divided by the mass of the star. And you can see a very well-defined velocity for the outflow. The red curve here is what we have in case of a successful jet. There is more material here, but this is a jet, so I do not care about the ultra-relativistic material. But all this material here, from Lorentz factor of about 3 or 4, up to the point, this is a square root of the energy deposited into the cocoon divided by the mass of the star, we have a roughly constant amount of energy per unit of logarithmic velocity. The different cases here is these two jets are jets which are choked. I will not talk about choked jets. We already talked about choked jets quite a bit. So the conclusion from this is a single simulation. It's only one case, but at least in this specific simulation, when a jet is exploding a star, we expect the material to go out over a wide range of velocities. Well, what I mostly care about is that there is a comparable amount of energy in mildly relativistic velocities and in subrelativistic velocities. Now, these different materials have a very different observational signature. The mildly relativistic material is expected to produce first absorption lines that we see during the early phase of the supernovae. And this absorption line will later fade away as this material is becoming optically thin. This is what Svi talked about. And second, and probably more easier to detect, it's expected to produce a very, very bright radio emission. The radio emission of shock driven into the circumburst material is expected to go like something like beta gamma to the fifth. So if there is a lot of energy in mildly relativistic material, it's extremely bright in the radio. The subrelativistic material is expected to give us a supernovae. So we can estimate the energy in this region from the radio and from absorption lines, and the energy in this region is simply estimated from the supernova. So this is a single case. What happens when you look at different cases? So here you see a range of simulations varying the properties of the jet, the structure of the density of the star in the inner parts, outer parts. Anything we did, we get exactly the same or roughly the same result, which is the same amount of energy where square root of the velocity of square root the energy divided by the mass of the star, and the same amount of energy with a Lorentz factor of about 3. This is energy, this is for velocity divided by the velocity of the supernova. So this is not a Lorentz factor of 100. This is about Lorentz factor of 3 or something like this. And the reason is just what I said before. We have the inner cocoon and the outer cocoon. They always have similar properties, and roughly the same physics works regardless of the properties of the jet and the exact structure of the star. So now we have a very strong prediction of an observational signature that we should see if the jet is indeed the only source of energy of GRB and the associated supernovae. So these are the observations. This is from a paper by Paolo Mazzali, and what you can see here is the following. This is the energy in the radio. This is the energy in the supernovae, kinetic energy. So roughly, this is a mildly relativistic material, and this is the subrelativistic material. Sorry?
Ciao.
Sorry, can you hear me?
It's okay.
It's okay?
Yes.
Okay.
Keep going.
Thanks. So what you see here is this line is where the energy in the subrelativistic and mildly relativistic material is comparable. And you can see that always in GRBs, these are long GRBs, these are low luminosity GRBs, always in GRBs, when there is an observed supernova, we can measure the energy. The energy in the relativistic and subrelativistic material is much lower than the energy in the supernova. Typically, at least one order of magnitude lower, and sometimes more than that. And if we give a number, so you see that the supernovae energy is usually around 10 to the 52 ergs, almost 10 to the 53 ergs. And the energy in the GRB itself is ranging from about 10 to the 51 erg for the long GRBs and much lower than that for the low luminosity GRBs. So as you can see, these observations are in strong contradiction to the prediction of a jet-induced supernovae. Here you can see a similar plot. What you see here is actual measurement, most of them done by Paolo Mazzali, of the distribution of velocities in the supernovae. This is the region where the supernovae is, and these are constraints from radio. This one is for probably the best observed GRB supernovae 030329, and this one from famous 98 BW. And again, if this the GRB was produced and the supernova produced from the same jet, then we would expect the energy of the GRBs to be of the same order as the energy of the supernova. And what happened, what we did next was actually having a simulation with two sources of energy. One is a spherical explosion with energy of a few times 10 to the 52 ergs, similar to what we have in observing a supernova, and the other is a jet which deposits in the cocoon about 10 to the 51 ergs. And as you can see, I will not get into the reason, but the distribution of the observer at the end, which is a solid black line here, is almost a superposition of the two distributions. And this is exactly what we see in the observations. So we see a peak near the supernovae, and then something which is well, it's hard to know if it's roughly constant or not, but in Lorentz factor larger than 1, there is an energy which is about 1 or 2 orders of magnitude less. So my conclusion is the following: whatever is exploding or producing the GRB supernovae must have two different sources of energy. These sources can be related. The energy which is going to the relativistic material is extremely collimated, and it's about 10 to the 51 ergs. The Newtonian, there is the second source is wide, possibly spherical, not necessarily spherical, but much wider than the relativistic source. Its energy is between 1 and 5, 10 to the 52 ergs, and it's subrelativistic. So as I said, it can be related, the two sources. So one possible explanation, which is not by no means the favorite one or anything, is just having, for example, an accretion disk with a wind that is 10 to 100 times more energetic than the narrow jet, which is launched by the accretion onto the central object. And I think that this is a constraint that each model should fulfill. Now, I will just put one slide about the energy budget. And I think that this is something that often people that I talk to don't think about. If we look at long GRBs, if the source of energy is accretion, then we're talking about 1 solar mass of accretion onto the central object. Now, this is about two orders of magnitude more energy available in principle in the accretion if the efficiency is 100%. Only 1% is going to the wide Newtonian outflow, and only 0.1%, 10 to the minus 3 of the accreted energy is going out in the form of relativistic jet. If we look at GW170817, which is the merger next to us, the only one we actually saw, here we know that there was an accretion disk with about 0.1 solar mass. We know that there was a Newtonian outflow with about 10 to the 51 ergs, which is about 1% of the accreted energy. And we also measured the energy of the jet based mostly on radio observations and X-ray observations. And the energy there will actually constrain this is the jet with the best constraint on its opening angle. So we can actually measure the total energy, and the total energy was about 10 to the 50 ergs, again 10 to the minus 3. So I would say that this similarity between the energy budgets of long and short GRBs is at least suggestive that the sources, that the engines might be the same. Okay. How much time do I have, Tzvi?
Another 20 minutes.
Okay. Oh, I will probably be done earlier than that. So the next question I'm asking is the following. We know that there is a jet, and we know that the jet is launched by a long engine that works for a long time. And when we say engine, we mean that the launching time of the jet is much, much longer than the dynamical time of the engine. So the dynamical time of the engine is of the order of milliseconds or 10 milliseconds. And the duration of the GRB is reflecting the duration of the launching of the jet, which is in long GRBs, tens of seconds, and in short GRBs, about 1 second. And we know that the engine is very variable, or at least we don't know that the engine is very variable. We know that the gamma ray emission is very variable, and this variability can be a result either of fluctuation in the power from the engine, or it can be it can be induced, for example, by interaction of the jet with a surrounding medium. It was actually shown that a continuous injection of energy in the engine and interaction with a medium can produce this variability. It can be something to do with the efficiency at which the power of the engine is converted to gamma rays. But at the end of the day, we expect that the overall envelope of the emission from the prompt emission will reflect some other the temporal evolution, the long-term temporal evolution of the engine. What do I mean? For example, let's assume that our engine is a magnetar, fast rotating magnetar, and this magnetar is injecting its energy via slowing down. In this case, we expect to have continuous, roughly constant, up to some possible fluctuations due to baryon loading or something like that, roughly constant energy input up to some time. And at times longer than that, the energy input of the engine is expected to decay roughly like t to the -2. Another possibility is to have an accretion. So when there is a disk, this disk is usually consumed over some time where the accretion rate is roughly constant. And then when most of the disk is consumed, we expect the accretion to slowly, or not surely slowly, but it is expected to decay roughly as a power law over the duration of the constant accretion. Also, if we look at the star and there is a continuous feeding into an accretion disk, we expect the feeding not to stop immediately, but roughly the duration over which the power, the material is fed into the disk, it should be the shut off or the decay of this feeding is supposed to be of the same order. The time scale for decay is supposed to be of the same order of the duration of the activity. So a naive expectation would be that we will be able to see this decay in the power of the engine imprinted into the prompt gamma rays, which, as we know, are very efficient. So they release a significant fraction of the jet energy. So they must reflect its duration, its power. Okay, this is what I just said. So what I mean in that is that on top of the high variability, we expect to see some envelope of the luminosity. So there will be an evolution at early times. The average height of the pulses will be higher than at late time. Now, it's very difficult to see in a single burst. What you see here, this is already from 94. It's a gallery of different light curves. And you can see that each GRB is different from the other, and it's very erratic, and we cannot look at one burst and certainly we do not see this envelope in any single burst, but it's possible that we do not see because the variability in the efficiency or in maybe the engine starts and shut off and then start and shut off. It's possible if we have different episodes of accretion, or if we have some magnetic field which is arresting the accretion. So it's very difficult to see in any single object. So what I asked myself is, what happens if we actually stack all the light curves together? Now, I must say that I was quite sure that people did it before me. I'm still suspecting that I didn't find anything in the literature, but there is something. So the prompt emission is over there for 30 years now. Many different, there is a huge archive of the prompt emission of different GRBs. I didn't find anyone that did it before me, so I did it myself. If anyone knows about a reference of someone that actually generated what I call an average light curve of GRBs, I would be happy to know. So what I did was the following. I took very bright GRBs where I can easily reduce, subtract the background. I normalized all of them, so they have a same duration. So I basically divided the time by the duration of the burst. I normalized them so the total fluence was the same, and then I just sum everything that I get to get an average light curve. And I was curious, I didn't know what I'm going to see. So this is how the average light curve of long GRBs looks. This is an average of 49 brightest GRBs from the Patse burst. I took T90 to be larger than 10 seconds. It also gave me more. I got it's more likely that bursts which are longer are actually collapsors, and also there is more temporal structure that I can probe. And what you see is the following. If we look, this is after 10% of the duration of the burst and about 90%, the emission is roughly constant. So brighter pulses are not brighter than late pulses. The difference that you see here, which is starting slightly brighter, it's only slightly, it's about 30% brighter than the average, and decaying and ending slightly fainter, again about 30% lower, is probably due to the fact that pulses in long GRBs are known to rise fast and decay slowly. So my first bin here is including all the rise times of the first pulse in the burst, and this is probably mostly affected by the decay of the last pulse in the burst. But all together, I would say that I cannot see here any signature of the of slowly decaying or decaying over the time scale of the duration of the burst of the engine. So it's quite strange. I didn't expect it. It seems like something is shutting off over a duration which is much shorter than the duration of the burst. You can see this is a single case, but there are many like that. If you look, this is probably the last burst observed by Swift. I took a long bright burst, so there is the BAT emission is coincident with XRT, so I will know that the energy is not just that the energy emitted is not just going down outside of the BAT energy source, but to be sure that the actual energy emitted is going down. And you can see this is a linear plot, this is a log plot, and you can see that this is roughly the time where the decay starts after 50 seconds, and you can see that the emission drops by almost 2 orders of magnitude within about 10 seconds. If I look, what is the time for the energy to go to decay by, sorry, of the power of the gamma rays to decay by a factor of 2, it's about 2 seconds or 3 seconds. So it's much, much shorter than the duration of this burst. And there are many like that. So we see it in single bursts. And now I know that we see it also when we stack them all together. My next question was what's happening in short GRBs. So I took also, these are 36 brightest bursts of short GRBs, duration between ½ second and 2 seconds. And it's almost similar. The only difference is that in short GRBs, we do see here the rising at the beginning and the decay at the end. And this is probably has to do with the fact that first of all, in short GRBs, the bursts are harder and more symmetric. And second, in short GRBs, I hear in long GRBs, every beam here is about 1 second or 2 seconds or sometimes 5 seconds, and the pulses are much shorter than that. While in short GRBs, every beam here is less than ½ a second. So, or about less than ½ a second. So the first pulse is not always contained in the first beam. So again, we see in short and long GRBs roughly the same behavior in the sense that the engine is roughly constant in the average sense, not in each specific, not in each single burst necessarily, but in average, the engine is roughly constant for the duration of the emission, and then the gamma ray just stops. Now the gamma ray can stop for one of two reasons. Either the energy injection stops abruptly, which as I said is quite unexpected or strange, or that the efficiency drops abruptly for some reason. I don't know what this reason can be as well. So something must change in the jet itself, so the efficiency will drop so quickly. I have only this is only a question mark. I don't have actually any additional conclusion except for that whatever is producing long and short GRBs should know how to start and stop very rapidly, much faster than the duration of the activity of the engine. That's it. I will stop here and happy to answer any questions you have.
Thank you very much. I was just going to say that you ran out of time, but you didn't run out of time. Okay. Thank you very much for this very illuminating talks. Are there any questions?
I have one.
Well,
Excusez-moi, monsieur, je fais un tour des fauteuils, je regarde.
Remo?
There are many data that you have shown, and we have to work to see the correspondence between our approach and your considerations. And of course, the main difference is that we have a system composed of 3 parts: the supernova exploding in presence of a companion neutron star, and the supernova creating a new neutron star and the accretion process. I think in the next talk should be the one of Wang, and you will see a very interesting manifestation of our approach. I hope it will speak next. But let me go to the key point. The key point is we agree on what all your consideration about the cocoon, about the material which is generated by the supernova. But let's speak first about, we have to divide between GRB, which have JEV emission, and therefore black holes, from GRB, which have no JEV emission, and they are weaker, and they don't form a black hole. But I think the majority of the work, apart the statistic that we have shown that we will examine, applies to the one without jet emission, with the prompt radiation and the jet. The key point of difference is that we don't consider a jet, but we consider a new neutron star, a spinning neutron star with high magnetic field, which is injecting the energy in the cocoon. This is the key difference. And I would like very much to have spent the possibility to discuss this in detail with you, because that is the crucial difference. We see the new neutron star, the fast spinning, and you will see a beautiful example if Wang Yu will speak next. But let me say that all the consideration that you have shown, we will give soon, in the next week or so, an interpretation of our model, and to have the occasion to think about the summer school to explain everything of this to the many students. But thank you very much for this very, very interesting talk. I, of course, follow the literature and the consideration about the cocoon. The key difference is that we have a very fast spinning magnetic field pulsar, but Jorge will take over. I have now to detach myself because I'm preparing to come to the villa at 2 o'clock.
Thank you very much.
Okay, bonne journée, Remo. Hope you to see you here soon. Jorge, you have a question.
Thank you. Yes, there's one question is related to the origin of the energy powering the jet. Because in this accretion, as you showed, this estimate of one solar mass of accreted mass, maybe that could be higher for higher energy GRBs, if depending, of course, on the energy of the jet. But that would imply for the time scale a very high accretion rate. If I'm not mistaken, that would be of the order of 10 to minus 1 solar masses per second, assuming it's constant. If it is not constant, it would mean that at the beginning you should have something even higher than 0.1 solar masses per second. But I don't know how you can get that from typical fallback. Is you have something like 2 or 3 orders of magnitude less than that. So can you tell us a little bit about this kind of process that you expect to power such a huge accretion rate?
Talk about the long GRBs?
Yes.
So in principle, if there is depending on the angular momentum profile of the star, but in principle, you can have a rather rapid fall of material on a disk at something like 20-50 kilometers around the central black hole, which is formed during the collapse of the core. And in principle, the fall on this disk can be fast enough. And also the accretion from this disk can be fast enough, because 0.1 solar mass, the disk is cooled by neutrinos. There is a generation of magnetic field, strong magnetic field via the MRI. And it was recently shown, not my work, but there is a work by a previous student of mine, Or Gottlieb, which is, I think, the first work that actually followed the collapsar model, including all the star and the propagation of the jet and the fall of the material and everything, and then they find accretion rates which are roughly at this level. Actually, their problem is that the jet is too strong. So they have some problems. They don't. What I said before when I said that you are accreting about about 0.1 solar mass per second, but the jet carries only something like 10 to the minus 4 solar m solar c square per second, and this is something that they don't know how to do in the simulations. Their jets are far too strong, but they get this high accretion rate, which depends on what is the profile that you take in your the interior part of the collapsing star.
I think that already in 2001, we have shown with Pawan Kumar and Ramesh Narayan that in low GRBs you probably form a accretion disk, which is the size of a few hundred Rg, and the time scale for the accretion of such an accretion disk could correspond more or less to the duration of long GRBs. It depends, as you just said, it depends critically on the angular momentum profile of the collapsing star, and we don't exactly know what it is, but for reasonable models, you can get few hundred Rg, which will correspond to tenths of seconds of accretion, and this is consistent with this picture.
But what do you have in the jet inside?
The jet is the jet is, there is a very recent work by that Udi just mentioned by Paul Gottlieb and Tchaikovsky, who have shown that such an accretion disk will produce jet, and as Udi mentioned, their jet is very powerful, almost too powerful. So yes, the accretion disk produces jets. This is what we learn, and not only we learn, we see such jets all the time in the sky in AGNs. We know that accretion, even if we don't know how to produce the jets on the computer, nature knows how to produce it because we see accretion disks and jets in AGNs. This is a fact that we see. Now, in the recent progress is that there are examples of simulations which actually manage to produce jets. So yes, we do produce jets. If you ask me if I produce jets, no, I didn't produce jet myself, but colleagues produced this.
The jet is basically produced by a process.
Mechanism production is critical to fit to have this relation between these numbers.
It depends on the magnetic field evolution.
How do you convert the energy into the energy of the jet? And this
Can I intervene a moment? The case of active galactic nuclei, I don't know if you followed the very beautiful talk yesterday at the end, and Brian Punsley showed how to create the jet in M87, and we know also how to create that from the rotation of the black hole. Therefore, that in M87 there is a jet is no doubt, and we have also the same mechanism which create the emission in the JEV radiation and in the GRB. But I hope that Olga has shown that we have some jet in the JEV in the GRB, but not in the X-ray. In the X-ray, we have just the magnetic neutron star. I hope this will clarify. Definitely jet in M87, they're spectacular, and they come out from the magnetosphere of our solution, of the world solution. And we have the detail of this. I hope Olga has shown you that.
Okay, Udi, do you have any more answers, or are there any more questions from the audience? I don't see any. So,
hello, I have a very short question. How do you explain this? Hello, can I have a question? Very short one.
Hello?
Please do it.
Oh, yeah. How do you explain this ratio between the two energy? One is a Newtonian wide outflow, the other is relativity coordinate outflow. It's almost a 1 order magnitude difference.
I don't know. So
no, the question is, if you all so many pairs, if I understand you list,
okay.
they show up this 1 order magnitude difference. So if this model conclude all this, it must be some reason for it.
I agree that there must be some reason, but we need to understand how the engine works in order to know. For example, one possibility, as I just said before, is that the wind from the accretion disk is such that, there is 1 order of magnitude more energy in the Newtonian subrelativistic wind compared to the relativistic jet. We know actually we have a better constraint on what's happening in GW 17017 or 817 compared to what happened in long GRBs, because we saw the gravitational wave from the merger. We have a very good estimate of the mass that was ejected from the wind itself and from the merger itself. And it most likely, it's not necessarily the case, but it's almost certainly the case, that the energy in the most of the at least slowest material that were ejected during the merger is coming from the disk. And this energy in this material is roughly 10 to the 51 ergs. And we also know that later there was a relativistic jet. We saw it. We don't know how it was formed, but we know that somewhere during this process that included a disk and a compact object, a jet was formed. So at least in this case, the ratios, all these values in GW17 or 17 are very robust. The mass in the disk was something like 0.1 solar masses. The energy in the material, relativistic material, which was roughly spherical, was 10 to the 51 ergs, and the energy in the jet was about, and the energy in the jet was about 10 to the 50 ergs. So natures know how to do that. I don't yet.
Okay, I think that we are running out of time, so we should move to the next talk. Thank you again very much for this very interesting results. And we continue now with a talk on Zoom, a second talk on Zoom by Liang Li. Please connect.
Hello?
Hello. Yes, you are connected now. Please connect your screen. So you have 35 minutes, and I will alert you 5 minutes before the end of the time slot.
Hello?
Yes, yes.
Can you hear me?
We can hear you, but we don't see your screen.
Can you see my screen now?
We don't see your screen. Please share your screen.
Wait a second. Let's share my screen.
Hello.
Hello. Maybe I can, the next speaker, maybe Wang Yu can force than me, okay? I will change my computer.
Maybe we could change to Gregory, yes. Maybe we could change to Gregory and then you will give it your talk after.
When excuse me, Wang Yu is when is speaking, Wang Yu?
I'm the next one. I'm the next one.
Okay, then start now and ask the system manager to help Liang Li.
No problem. I don't know why.
You start your Wang Yu.
Okay.
Gregory, maybe we should switch to you.
Ruffini is proposing to have Wang Yu. Maybe
Oh, Wang Yu?
Wang Yu, maybe this is not the last version.
No, this is not.
There was change. So I bring the last version of Wang Yu. So Ruffini is proposing to have Wang Yu.
So I'm going to share my screen, okay?
Yes, now Wang Yu is speaking.
I don't understand. Okay.
I can show you the latest version.
The latest version is, sorry, there was a change. Oh, so we have 3 speakers now. So we have Wang Yu, Liang Li, and Gregory. Okay, so Wang Yu, can you please go ahead?
Yes, this is Wang Yu.
And we have 20 minutes, and I'll give you a warning 5 minutes before the end.
Okay.
Maybe it's better you give 35 to Wang Yu and little less to Liang Li.
Okay. So 35.
Okay, I'm going to talk. Let me set up my audio. My screen is on, yes? Can you see my slides, the video?
Yes.
Yeah, good.
Yes, we can.
Yeah, if you remember, I took this video with Professor Ruffini when we were at Tsinghua University. Bike sharing was very popular in China at that time, and there were several brands operating by different colors of bikes. And Professor Ruffini saw the bike and told me he wanted to ride it. So we took the chance. That day we needed to go from Yao's mathematical center to the astronomy department. The Tsinghua campus is very big, and it was just rained that day. So it was very pleasant to ride in the garden-like campus. And here are 2 more photos. You see Professor Ruffini was happy. And you see the color of his trousers, it matches the color of the bike. Good. Because Professor Ruffini and I have, so first let me show many pictures that Professor Ruffini visited China because I'm a Chinese. So Professor Ruffini and I have been to Tsinghua University several times, mainly because of the invitation from Yao Xintong, Professor Xintong Yao. And accumulatedly, I think we have lived there. We always live in a hotel inside the campus for, I think, for 1 month or 2. This photo was taken by a CCTV, our national television station, a CCTV journalist after a dinner that in a very fancy place. And from left to right is...
but you are speaking also about the latest result, I hope, no?
I speak a summary, but not the latest result. But I can talk about it. Okay.
Yes, yes, that is very important because it's related to the talk of Nakar.
So from left to right is Jorge Rueda, then Raymond Ruffini, then Xintong Yao, Sheng Xue, and me, Wang. And we, in exactly, I think 3 years ago of this month, May 2019, we had a very complicated trip to China. At the first, we went to Shanghai to visit the Shanghai Jiao Tong University and the TDD Center. Now in this photo, Professor Ruffini was talking to Professor Hongjian He and his students about his work on Boson star and his trip to China more than 20 years ago. Then the next day, we left for Nanjing, where we gave presentations at the Gamma Ray Burst conference held at Nanjing University. Then we left again for Beijing to Tsinghua University again. The photo on the right was taken at the Nanjing South Railway Station, where we bought the chicken rolls and the coffee from the KFC because we were in a hurry to catch the train. And Professor Ruffini was holding a coffee shop from KFC, which he told me he had not eaten for decades. And while waiting for the train, I remember Professor Ruffini talking about bringing his son Yakbo to have a trip in China, which I hope it will come true after the pandemic. Then this photo was taken when we arrived in Tsinghua. We visited the astronomy department of Tsinghua University, and where we happened to meet Professor T.P. Li. They too were so happy to see each other again, I think maybe after 20 years. And they hugged each other immediately after seeing each other. The photo on the right side, including Professor Mao Sude, they were discussing about the works and the collaborations. When we left the astronomy department, Professor T.P. Li told me that he admired Professor Ruffini for being nearly 80 years old, but still very active. Today, Professor Ruffini just is 1 day over 80 years old and still active. I'm happy with it. Then afterwards, we returned to Nanjing to the conference and celebrated Professor Ruffini's 77 years old birthday between the sessions. I think this is the video. This is Professor Bing Zhang led the birthday song. Happy birthday to you. Yes, exactly 3 years ago. Okay, then after the Nanjing meeting, we were invited by Professor Ye-Fei Yuan and Professor Yifu Cai to the University of Science and Technology of China. This is a group photo after dinner. USTC is one of the ICRA members and having a decades-long relationship. This visit also opened the joint USTC Frb University ICRANet PhD program that is now in operation. And after, in the later 2019, Professor Ruffini went back to China again for the opening of the United Center for Gravitational Wave Physics, led by Professor Anzhong Wang, and signed a collaboration agreement. So as you can see, we, ICRANet and China, communicate very frequently, and after 2020, it is not convenient to travel internationally because of the pandemic. I have noticed recently an increase of the flights from China to Europe, which is a good sign. Hope we will return to the normal communication soon. Then I'm going to give a brief review of the binary driven hypernova that has been developed for a decade almost. So this photo is, I think, a New Year's photo, having dinner in Professor Ruffini's apartment in Pescara. Yeah. Professor Jorge Rueda just gave a quite detailed talk on binary driven hypernova. So my plan was to go through the papers that we published in recent years. So first, as articles related to the binary driven hypernova's picture, physical picture. So Rueda and Ruffini 2012 has been the first article to consider accretion of supernova ejector onto a very close by companion star of the binary period of a few minutes. And it gives the physical picture and the theoretical theoretical architecture of a simple one-dimensional model that calculates the boundary height for your critical accretion. I think the details Jorge has given some hours ago. Then Friday et al. 2014 numerically simulated for the first time the corresponding BdHN accretion. Vecella et al. 2015 went one step further, performing two-dimensional numerical simulation and incorporating the angular momentum transportation from the neutron star or from supernova ejected to the neutron star. Then Fire et al. 2015 demonstrated that most BdHN with tight orbits remain bound after the explosion and accretion, even when a large amount of the mass is lost and a large peak of velocity is induced. Then Vecella et al. 2016 performed the three-dimensional numerical simulations of the BdHN process, which were further upgraded and improved in Vecella et al. 2019 by smooth particle hydrodynamic simulations. And from the observational side, we have made a lot of examples demonstrate the scenario in Luca et al. 2012, Ruffini 2005, Wang 2019. Actually, there are many papers. So this is a simulation of two stars. These are the 3D simulations that are performed by Vecella et al. 2019, viewed from the equator or from the polar. Then the second part is the papers related to the inner engine. So once the neutron star reaches the critical mass of fast rotating black hole forms, which contains sufficient rotational energy, more than 10 to 54 to power a GRB. Ruffini et al. 2019 and Rueda et al. 2020 proposed an efficient way to extract energy from the newborn black hole. The inner engine is composed of the newborn rotating black hole surrounded by the magnetic field inherited from the collapse of the neutron star. For an aligned magnetic field with angular momentum from the solution, an electric field is induced by the gravity-magnetic interaction as described by the water solution. The media around the black hole provides a sufficient amount of ionized particles that are accelerated to ultra-relativistic energies by that very high induced electric field, thereby emitting synchrotron and curvature radiation at the expense of the black hole rotational energy. So this picture is the emission at different angles. At the center, it accelerates to very high energy and emits the ultra high energy cosmic ray. And when the angle increases, the energy decreases as well. And also the third part is the articles related to the propagation of the plasma and the prompt emission and the afterglow. So following the papers of the functional model developed from 1999 till 2008, we have several papers investigated the ultra-relativistic prompt emission phase. So after forming the black hole, the electric field is critical, generating a optically thick electron-positron plasma by the vacuum polarization. Also, we have the accretion still going on. The plasma expands and self-accretes to the ultra-relativistic speed, and finally, the energy is released as a prompt emission. And Rueda et al. 2018, here Wang et al. 2018, Ruffini 2018, and other papers, we investigated the afterglow that along with the conversion of the kinetic energy of the supernova shell, into radiation, the spin down energy of the newborn neutron star injects energy to the expanding supernova ejector, emitting the observed afterglow by the synchrotron mission. And this model naturally includes the supernova, which appears and be observed at the optical band about 2 weeks after the GRB trip time. And this is a video, a movie clip from the movie Correspondence. The director is very, very famous. I think everyone, let's say more than 90% of person watched his movie before. Tornatore. And Professor Ruffini was the scientific advisor. The main actress of this movie is the PhD students working on this binary drive hypernova.
Fundamentally derives from the study of dead stars.
Yeah, boy.
Topic event that marks the end of a star, explosion or collapse of a supernova.
And you try to go to the latest result.
Okay, I did not prepare, but let me open the paper and say something, okay?
Yes, because that is really the important point to show to Nakar and to everyone and to Jorge and to Zvi.
So this is a paper, this one, yes. Actually, we are working on 2 papers recently. This is one of them. This is a typical BdHN 2, which means it's from the binary, but the accretion doesn't induce the companion neutron star to a black hole, but to a massive black hole, because accreting mass is not enough. And we know also from Jorge's presentation, we have these 2 stars accreting. So the left side, the blue one, is a supernova explosion, and the shell has been expelled to the certain expelled around. So some parts are accreted by the companion neutron star, so this red part. And because of they are rotating, this companion neutron star, while it is accreting, it also expels some matter back to the supernova center, where has a newborn neutron star, so the blue point. So therefore, we will see the signals of 2 kinds of accretion: the accretion onto the newly born neutron star at the blue center, and the accretion onto the companion neutron star. Now, these are the signal here shown on the light curve. Okay, and also from the simulation, we know more or less the accretion rate 10 to -3, 10 to -4, 10 to -2 solar mass per second. And from this accretion rate, we can compute the luminosity, which corresponds to the luminosity that's observed in these 2 pulses. Then after having so this is a prompt emission. Then we are going to afterglow. So we know we have a newly born neutron star found at this blue point because of supernova explosion. This newborn neutron star has a very high rotational speed, always millisecond period. So this millisecond pulse emits energy to the outflow outside and powers the afterglow. So we use this model, also the fallback accretion was Let me see where's our spectral fitting. So here are the formula. So we fit the afterglow by the slow move, not slow move, minor relativistic moving supernova ejector part, the transparent part, with energy injection from the newly born neutron star, and then we fit here the X-rays, optical, the radio signals. But this burst is observed by Hess, which observes TeV, TeV radiations. But our model, this synchrotron model predicts, simulates this black line on this spectrum, and this blue one is synchrotron self-competent. Both cannot explain the green point, which is observed by Hess at the TeV. So for the TeV radiation, I think we know it's related to X-ray because they have very similar polar decay index. But in our opinion, it's also more related to the central engine because I think in my slides I showed the different angle, we have different energy. But this is not written in this paper. So this is a typical example. And now I'm going to, maybe Professor Ruffini wants me to show another one. Is this one? This one is not finished. This is the GRB 171205. It's a low luminosity GRB. So we see the luminosity of 10 to 47 per second continuing for 200, 300 seconds. Then it decays normally, not like other off-axis GRBs. It decays normally and with a plateau, then decays also normal for X-ray. Okay, for X-ray with this power law index -1. Okay, but this GRB has its specialties that first it has the optical at 10 to 4 seconds. It's very high optical emission. And then later it's 10 to 6 seconds. We know it's from supernova. This 10 to 2 and from Ehud Nakar's paper, they found a thermal component evolving from 10 to 2 seconds, almost here, 70 keV, 80 or 70 EV, 80 EV. It jobs till 4 days to the optical. The optical is fully explained by the thermal component, but for the X-ray, it's about 5%. For the X-ray, it has some 5% thermal, 95% non-thermal. And for the optical, it's almost all thermal. And the thermal before 4 days and the thermal after 4 days, they are different from Ehud Nakar because they found that they have different elements from the nuclear synthesis model. And they interpret the thermal component evolving before 4 days is due to the expanding of the cocoon, the material accelerated by the jet. Okay, then later, after 4 days, the cocoon still continues to emit, but the supernova optical predominates it because the nickel decay and the diffusion time peaks at this time. So in our picture, we also interpreted this burst as also a single star, just as the burst of a neutron star. And then we also consider this cocoon because always there's a shell of the progenitor star remaining there. So the plasma, the outflow must pass it. So the difference is we have it. Difference is our interpretation of the optical. The X-ray afterglow uses a minor relativistic supernova ejector instead of the that very fast ultra-relativist gamma 100 jet. And we found that if we extrapolate back, for example, this pattern, this decaying, the X-ray decaying red points back, it always coincides the beginning, not always, but most of the time coincides with the beginning of the burst. This is like a supernova, a newly born neutron star started to emit here in the very beginning and lose its rotational energy. Sometimes it's not transparent because some material outside. And finally, at a given point after the plateau, it starts to dominate the radiation. See, it's here. And this pulsar can be dipole, can be quadrupole. It's a new pulsar. Sometimes we need a quadrupole because of the decay index at a later time, more than 10 to 14 to 5 seconds, is not -2. Sometimes it's a decay index -1.2 and -1.5. So you need a higher dimensional high dimension polar radiation to account for different decay index. And then for having a neutron star initially emitting so high luminosity at 10 to 47 per second, we need it to be faster spinning. So we considered how to spin it up. And this is also natural in our picture because we have the equation, we have the fallback equation. And in this theoretical part, we compute how long it takes, and is it possible to spin a non-rotating star or slow rotating neutron star to a faster millisecond rotating star, and it is possible, and we have all the values here. I think that's enough, Professor.
Yes. Very nice. So, and the key point here again is there is no jet, but there is the emission of the newborn pulsar from the supernova, from the accretion of the material of the supernova, like Jorge has shown. These are beautiful results and clarify the different role of the new neutron star and the black hole. In this system, the black hole is not present, no JEV radiation, but is dominated by the new neutron star in both systems. And you see the slowing down of the new neutron star giving the X-ray afterglow. The backbone of the system is the X-ray afterglow. Okay, if you have any other picture that you wanted to show after Tornatoris, okay, but I thought this was very important to show.
Yeah, okay.
If you have any other picture, show.
No, I don't have. I only prepared this.
Beautiful. And we invite everyone to go and see the Tornatore movie about the BdHN.
Yeah, you can watch the movie together in the evening.
Okay.
Yeah. Okay, I turn off my screen.
Thank you very much.
Okay, thank you.
Okay, thank you very much. Now to Liang. I hope you can share your screen now.
Sorry, but
you cannot share your screen.
Sorry, the problem in my computer. I'm not changing. It's another computer.
So we'll give you one more chance. Is Gregory available? Gregory, are you online? Oh, you manage. Fantastic. Okay.
Can you use? Okay.
Yes, we can see it. Okay. So you have now 15 minutes.
Okay. Thank you.
Okay, thank you.
Okay.
Go on.
Okay. Okay. First of all, I would like to say happy birthday, Professor. My topic is Bayesian gamma ray source spectral analysis in the BdHN gamma ray burst. My collaborator, Professor Ruffini, Mulati, and Professor Olga Wang, Professor Shakeri. And let's starting with the observation. As we know, the typical from gamma ray spectrum can be well described by an empirical function known as the bound function. The bound function, there are several model parameters. The low energy, two polar low energy polar and high energy polar collected by peak energy. And in some cases, if the lack high photons in the high energy region, the beta index cannot be well constrained, then the bound function should be replaced by a cut-off or functions. The physics origin of these empirical functions have not yet understood. More likely relate to line thermal emission origin like the synchrotron radiation. The typical value of these model parameters from the observation by Fermi give the alpha or around the -1, and beta index around -2.2, peak energy around 215 keV. And in of very few cases, we can observe the very narrow peak. This narrow peak usually can be well fitting by a Planck function. The Planck function, there are only two model parameters, temperature and the amplitude. This is the case, like this case, OLI-P. The Bayesian fitting can be a single polar plus a dominant black body component. The Planck function have a clear physics origin related to a thermal emission, thermal component from a augment from a photosphere emission. And then the temperature typical range from the 13 to the 115 keV. So in some other case, very interesting there, we can observe the hybrid spectrum, namely the line thermal component and including the line thermal component and the thermal component simultaneously observed. Like this case, 110728, the Bayesian fitting can be fitting by a band-like emission component plus a sub-dominant black body emission component. So this picture, cartoon picture, showed describe the BdHN models. The BdHN models was first mentioned, developed by Professor Olga and Professor Ruffini in 2008 in a paper published in BdHN. And as predicted by BdHN model, there are several different physics processes, and these different physical processes might have different spectral property or temperature property from the observations. So why BdHN models? There are two significant advantages. The first one is the BdHN model is based on the binary star system. Binary star system which has a very high observed rate as compared to the single star system, like a traditional Frb model. And the second one, the BdHN model can naturally explain why gamma rays are associated with a supernovae explosion. So my talk today relates to several of recent projects of our teams. So all our spectral analysis is based on the Bayesian approach, using 3ML package. The 3ML package is developed by Fermi team a few years ago. The parameter estimation, we use the Bayesian inference plus monocolor simulation. And we set the typical value of the model parameter observed by Fermi was a prior distribution when we perform a Monte Carlo simulation. And there are different BdHN class and defined by different projector and different energy ranges. And we have analyzed in detail, the spectral analysis in detail of 21 BdHN bursts. So we our spectral analysis starting with a very famous burst, Latin 114C. The first type emission was observed by magical telescope. We found several different emissions might relate to different physical process. Like in the Latin 114C, we identify 3 emissions. The first emission, namely the precursor, related to a neutron star rise on the creation of the new neutron star. And in emission 1, there are 3 major events: the formulation of the black hole, and the onset of gel emission, and the onset of the neutron relativity problem emission. And the emission 3, we observe the cavity cover out related to cover out in the supernova injected by the black hole formulation. And we also observed the similar result. We also observed in other several very bright sources like 606, 25B and 605A and 1304, 27A. Our logic is, the main step of our spectral analysis is we starting with a relevant wide time interval. When a sample component is observed, we then look deep and short into the intervals. So the group behavior predicted by the BdHN models can be summarized. I mean, the long term time scale and the multi-wavelength luminosity evolution predicted by BdHN can be summarized. Initially, we observe a UPE phase related to black hole rise, then follow a neutron rise, then the main UPE phase, then the cavity, and then follow the hot and the soft exoflare, and the last the afterglow emission. So when we look at the UPE1 phase, we found that there's when look shortening the shortening the time interval in during the UP1, we found some similarity structure. Moreover, we also found some similar properties in different sources, like the duration, like the temperature, like the astronomical energy. This observed property similar in the different BdHN1 source. So then we, after the UPE1 phase, then we follow the neutron rise. The neutron rise show a line thermal emission spectral behavior, such we can fit in by like we can fit in the spectral with Temporal models. Then for main UPE phase, we observe the very bright thermal component in the UPE2 phase. Because the thermal component is so bright, we have performed 5 successful time integral for the UPE phase and look shorter and shorter, look and deep and deep. Then we found a self-similarity. Also, we found a self-similarity structure of the spectral analysis during the UPE2 phase. Then we summarize all the information in this table, and including the fitting result and analyzing and the statistical values. And we also found the temperature and the luminosity during the UPE2 phase, and percent of single power decay. And the similar result also found in the other sources like 60625B and 605A. Then after UPE2 phase, it follows the cavity emission component. The cavity, the spectrum of the cavity can be fitting with featureless catapult model indicate line thermal emission component. Then the last, the afterglow, we found all of the BdHN one burst can be fitting with a single power model with a power index around minus 1.3. And moreover, we also found that after different BdHN bursts have different after emissions. In the BdHN one, we found the supernovae emission typically are much lower than the after emission. However, in the BdHN two, the supernovae emission is still lower than the after emission, but not as much lower as in the BdHN one. And very interesting in the BdHN three, both the supernovae emission typically are much higher than the after emission. Okay, this is my conclusion. We identified several different spectral components in several bright gamma bursts. And the temperature and the immunity in the UP1 and the UP2 phase present a power decay. This observation can be well explained with the framework of the BdHN model. We found different BdHN bursts have different after emission properties. Okay, last, I would like to say many thanks to Professor Ruffini. And in 2013, I started with my PhD research funded by Erasmus program. And Professor Ruffini is the chair of this PhD program. And thank you so much, and thank you so much and the committee for selecting me. And in 2015, I would like to thank you for your providing me with the opportunity to work with you and your team when I stayed in Piscala for 6 months of my PhD mobility. I also have very lucky to be a faculty member of the eCollider since 2008. Thank you so much for teaching me how to do the physics, not only data analysis. So this is the picture. The left is a picture as it has already shown by Professor Zhang in the morning. 3 years ago, we celebrated your birthday in Nanjing when we participated the Nanjing Gamma Ray burst meeting. On the left, our photos together, and you write some note to me. Happy birthday. Thanks.
Thank you so much. Thank you so much.
Okay.
Thank you. Thank you again.
Thank you.
And I hope everybody will see how beautiful are the spectra and the different epoch and the different process going on in GRB. Not only the 3 basic components, but also the spectral characteristic of each epoch. And you have been the one to do the statistical analysis like anybody else in the world. Therefore, we are grateful to you for all this work. And let's keep going. Let's keep going, because now that we understand the GRB, there is much physics to be presented, because we have time scale of the order of 10⁻14 seconds in the UP, which is total new physics.
Okay, good.
Okay.
Okay.
Okay, thank you very much for the presentation. And our next speaker will be Gregory Vereshchagin. I hope I pronounce your name correctly. If not, please correct me. So can you please share the screen and
Can you see my screen? Good afternoon, everyone.
Good, Gregory.
Yes. I cannot resist also to show you something in this special occasion. This is not the title of my talk, but just a few slides. Of course, much has been said, and I join the congratulations from all the parts of the world to Remo for his birthday. And just to mention that a lot of a lot of activities, scientific activities, first of all, were discussed during this meeting, which Remo initiated, and a lot of people were involved in these activities. I would like also to mention how organizational activities of Remo are extremely important and changed the lives of many people and changed the science in many countries, because it is well known that Remo was created the Group 9 in Sapienza, which later became International Center for Relativistic Astrophysics, founded with Abdus Salam and Fan Liji and many other important people. And later on, Riccardo Giacconi, obviously, and later on this became ICRANET, international organization, which we are happy to be part of. But just to illustrate how these organizational activities really happen, I show you a very brief example. This started for me in 2001, when I knew about, just got to know about the National Fellowship Program, which was organized by Italian Council of Research and funded by NATO. And this was a program for 6 months. The only requirement for people who liked to join this from all the ex-Soviet Union countries and from the Eastern Europe was to find the place in Italy where they like to do this research and to find a supervisor. So I looked on the internet and found this place called ICRA and found the name of its director. So I decided to write him a letter. It took me several days to write a letter. And surprisingly, after a few hours, I got the following answer. Certainly, I'm happy to be a supervisor. Next week, we're having an international conference to celebrate Enrico Fermi's work in astrophysics. Please do come. Well, those who know Remo, this is traditional style, he replies. It took me another few months to get positive decision from the committee for the fellowship and another 6 months to get the visa. So after all this time, finally, I ended up in Italy and I'm still here. And this was the first international meeting I participated. This was exactly 20 years ago when Remo celebrated his 60th birthday. I'm not on this photo because I'm simply behind it. I'm taking this photo. Therefore, from this, I will change to a scientific part of my presentation, and it's going to be devoted to one of the topics I'm involved in ICRANET from the beginning, which is about electron-positron plasmas, and especially non-equilibrium effects in these electron-positron plasmas. This is the overview of my talk. And to say why it is important, well, it's not necessary even to say that because you heard so many times during this meeting about electron-positron plasmas, and especially in this session devoted to gamma ray bursts, it's clear that electron-positron plasma plays a crucial role in dynamics and in emission in gamma ray bursts. But beside that, in other astrophysical processes, it plays an important role. And also in laboratory, there are strong efforts to create such a plasma, in particular related to interaction in ultra-strong, ultra-intense lasers between themselves and with targets. Such projects as ALI and Excel do aim to create electron-positron plasmas in laboratory. And of course, here we're talking about extremely short time scales, extremely small volumes, but at the same time, very high energy density, very high pressure. Therefore, these systems are clearly not in thermal equilibrium. Also, observed spectra in astrophysical sources show no thermal spectra. Therefore, we are talking about not equilibrium plasmas. Some of the material of the scientific material related to this electron-positron plasma in astrophysics and in laboratory is collected in this physics report paper, which we co-authored with Professor Ruffini and Shakeri some 10 years ago. Well, to describe non-equilibrium plasma, the basic approach is to use Boltzmann equation, namely kinetic equation for particle describing their distribution function in space and in energy or momentum in general, momentum space. All distribution function should depend on energy, coordinates, physical coordinates, but also on angles in momentum space and of course on time. It is more known binary interactions in such plasma, such as Compton scattering, for example, which are generally described by these collision integrals, which are multidimensional integrals in the phase space. So in principle, to describe evolution of electrons, positrons, photons, and other particles, eventually, it's important to solve these extremely complicated partial differential integral differential equations, which is a system of coupled equations, and their reaction rates actually depend on particle momenta and in general are also quite complicated functions. Less known are the three-particle interactions or triple interactions, which is typical example of Vereshchagin or double Compton interaction, for example, when we talk about electrons and positrons. And these are also described by collision integrals, but the number of integrals in the phase space increase, of course, because we talk about many more particles. This was an example of one of the first few calculations where we showed how triple interactions are important. This result was published in Physical Review Letters some 15 years ago, and it shows the time evolution of the number densities of electrons, positrons, photons, and their sum as function of time, starting.
Gregory, are you showing? We don't see your screen. You're aware of that?
You cannot see my screen? Oh, nobody told me.
No,
sorry.
No, we don't see your screen.
Oh,
We, but not the screen.
I'm sorry. Let me show again. Can you see it now?
Yes.
Oh.
And don't forget, Gregory.
Yes.
Don't forget to say the difference between the fire shell and the fireball.
Yes, exactly. I'm here on this point. Yes.
Exactly to show that to 3.
Yes. This is exactly this calculation. Can you see my screen now?
Yes.
Yes. Okay. So
yes,
this,
I can, but I don't know if they do.
Zvi, can you confirm you see my screen?
Clear.
Okay. Okay. So this is the calculation or solution of the Boltzmann equation for electrons, positrons, photon, and the number density is shown as function of time here. A number density of electrons, positrons, and photons. For upper part, you see the number density initially large for electrons and positrons. It means that we start with purely electron-positron plasma without photons, but eventually per creation produce photons. So with time the number increase, and then there is two possibility. If you take into account correctly triple interactions, direct and inverse ones, you end up eventually in thermal equilibrium with this plasma, and the evolution, kinetic evolution stops. Instead, if you neglect inverse triple interaction, what happens is that there is an increase in the number of photons, continuous increase, due to mainly double Compton and Vereshchagin radiation, but there is no counter process which may balance this. Therefore, indefinitely you will have a number of particle increase. It's strange enough, actually, that in the beginning of gamma ray burst searches, the spectrum registered of gamma burst was found to be very similar to thermal Vereshchagin spectrum, even before even before band spectrum was proposed as phenomenological feat, because in the band spectrum you have alpha is -1, and this is really the spectrum of thermal Vereshchagin. But when you do take into account inverse processes, you will see that this is This never happens. Bernstein is counterbalanced by its inverse process, and you don't have simply such evolution. The same can happen. It can be shown also for initial state where you start with only photons. Electron-positron plasma, electrons and positron will be eventually produced, and then the plasma will thermalize after certain time scale, which is here about 10 to the minus 12 seconds for a temperature about MEV. To describe the interactions you need, as I mentioned, to solve in principle the collision integrals, which are described by the matrix elements from quantum electrodynamics. So these are well known. Therefore, you can in principle construct a code which solves this equation out of first principle. And these are the principal reactions which are involved in the interactions between electrons and positrons. So we combine them as binary interactions on the left and triple interactions on the right. So of course, conservation laws have to be taken into account, and the code that we were using, in particular to solve these equations and to produce the result I've just shown, is described in a book we published together with my colleague Alexey Aksionov in 2017. This is the book. So the book is dedicated both to relativistic kinetic theory in general, describing interactions, electromagnetic interactions, but also gravitational interactions, and to numerical methods for solution of relativistic kinetic equations. The development of the code timeline is also quite long. So originally the code was designed for strange stars, and Vladimir Rusov and Mordechai Milgrom were involved in this work with Alexey Aksionov, and later on, but only this work was done for considering binary interactions only. So starting from 2006, roughly, we started to work with Alexey Aksionov on this and included triple interaction as well, and generalized this code for spherical symmetric case, anisotropic momentum case later on, and focused then on ultra-relativistic outflows, on degenerate plasma in general, and degeneracy effects in ultra high energy density plasma. It's important to mention that the thermalization process out of arbitrary non-equilibrium state generally proceed with two steps. First, so-called kinetic equilibrium forms, where the distribution function is described by two parameters, the temperature and the chemical potential of particles, and only later on, eventually it ends up in a thermal equilibrium where the chemical potential actually vanishes. This is a typical behavior for all the processes, also shown before. The presence of kinetic equilibrium manifests itself in various phenomena, particularly in Bose-Einstein condensation, which were studied in 2020 with a paper published in European Physical Letters. So you know very well that Bose-Einstein condensation is fundamental phenomenon which happens for bosons, and photons are bosons, with only difference that photons are massless particles, and in principle Bose condensation is not possible for photons in equilibrium, because the less temperature of photons is the less is the number of particles of photons. But instead, in non-equilibrium plasma, this can happen, and we show this following the original idea proposed by Zildovich back in 1979, that if, well, the original idea was that if you have hot photons interacting with low energy electrons, cold electrons basically, and if you have photon conserving process involved only, in particular Compton scattering, you will end up with a large number of photons which tend to stay at low energies, and this is exactly the prerequisite for forming Bose-Einstein state of photons. And namely, what you need is precisely a large number of photons, larger than the one compared to the one in kinetic equilibrium. We demonstrated that this process indeed can happen, starting from non-equilibrium distribution of photons at with sufficiently large number of photons. So you can see on the top here, with the solid green is the final thermal distribution for photon Planck spectrum essentially, and the dotted line shows initial spectrum of photons. So at the initial moment, about 10 minus 15 seconds, the spectrum looked like this. Later on, at 10 minus 11 seconds, you have a lot of photons compared to the thermal distribution at low energy, and instead roughly thermal distribution at high energy. And this is precisely the formation of Bose-Einstein condensate of photons. There is also a break at low energy, which demonstrate the dominance of three-particle interactions, and when three-particle interaction happen, Bose-Einstein condensate cannot form. And later on, eventually, the plasma thermalized to thermal equilibrium. Therefore, this is one of examples where when degenerate state can form, in particular for photons. Another example is the formation of electron-positron degenerate plasma, highly degenerate plasma, where due to Pauli blocking phenomenon, interaction rates are extremely suppressed. We showed that, well, of course, clearly looking at number density, energy density diagram, this means that we should go to high number density of particle with the same energy density. The highest number density is, the more degenerate the plasma is. This can be also at non-zero temperature, of course. But what we show in particular in this example, considering very large number of electrons and positrons, that if you have relatively soft photons initially, these photons cannot generate electron-positron pairs. Therefore, the reaction rates in this plasma will be completely blocked. Here we show a comparison of two cases. One, when we take into account Pauli blocking in the kinetic equation, and these are the solid lines. And one, we switch off artificially Pauli blocking, and these are the dashed curves. So without Pauli blocking, Boltzmann gas will evolve naturally to thermal equilibrium without any particular problems. Instead, what happens when degeneracy is on and reaction rates are blocked, you have no evolution up to a certain moment. Only later on, when you have enough photons which exceed the rest mass energy of electrons, they are capable to create electron-positron pairs. An avalanche creation of pairs happens. This opens up the phase space, and at this moment on, the avalanche thermalization happens very immediately, practically instant thermalization, and the plasma reaches thermal equilibrium. I think this phenomenon can be relevant mostly for such phenomena as described earlier on by Jorge when he was talking about pair creation in electric fields of collapsed object. This is similar situation when collapsed object is when the neutron star is in equilibrium, the phase space of electrons and positons is completely blocked, even in ultra strong electric fields. Therefore, no pair production can be feasible. Instead, when the gravitational collapse onsets, the phase space starts to open due to gravitational wave particularly, and this may allow you to create abundantly create pairs in this process, and therefore this can originate the emission of the collapsed object. I think this was the last slide. Here are my conclusions, simply general, saying that in kinetic evolution of the plasma, degeneracy plays an important role. Bose-Einstein condensation can form, and degeneracy is relevant for thermalization, which can proceed in avalanche-like manner. Of course, there is plenty of work to be done. In particular, consider non-uniform plasma. We only extended to spherical symmetric case so far, and not the general Boltzmann scheme. Fluctuations and the role of correlations was never studied, and this is an open question. And finally, quantum kinetic equation and the role of quantum alternative equations compared to classical Boltzmann equations is also to be studied. Thank you so much. And once more, congratulations to Remo.
Thanks. A notation to thank you for the beautiful talk, but I would like to stress the relevance of this to Zvi. Are you listening, Zvi?
Yes, yes, of course.
The differences between the far shell and the fireball, the key point are the three-body interaction that guarantees that the electron-positron pair keep a thermal distribution and evolve with a thermal way. This is a masterpiece due to Aksenov and to Gregory, and to me, of course. But the other point which you don't speak in this, which is essential to gamma ray burst, is the masterpiece of the masterpiece, which was done in ICRA and ICRANet between Jim Wilson and Xue, myself, and another collaborator of Jim, younger collaborator. And the key point is when you have an electron-positron plasma optically thick, Jim gave the equation of how it self-accelerates, and that is the basis for all GRB. Therefore, the first, the plus minus, keeping the thermal distribution, and then self-accelerating through the equations that Jim Wilson has given to us. And this work was possible thanks to the collaboration with Livermore. And I don't know if we will be able to have Grant Matthews, who was collaborating with Jim and with us on this problem. But the machine which characterized the far shell is E plus, E minus, thermal, self-acceleration, Jim Wilson, and everything else is just a detail. E plus, E minus with baryon load, without baryon load, the PEM poles and the PEM poles. This is the basis. Okay. Thank you again for showing this, and I hope in half an hour to be there.
Okay, we are looking to see you here. So are there questions on this last talk? No. We are a bit late, so we thank all the speakers of this session, and we'll move to the lunch break, and we'll join at 3 o'clock again.
So let's start, Professor Chiaravalli.
Okay. Okay. Can you see my slides? Hello?
Yes. Yes, clear.
Okay,
clear.
okay.
Yes.
So this is a talk, this is a summary of my talk. I will start with 2 slides on supernova taxonomy. Describe the main property gamma ray burst supernovae, progenitors in terms of.
En dessous du lit, ils y sont pas?
Je sais pas.
So I'm sorry. I'm listening. There is some background voice. I do not understand. Okay, the progenitor mass and size. I will expand the issue of gamma ray burst supernova rates, and then I go through the conclusions. I will skip the open issues. This is an important part of this talk, but unfortunately, I don't have time to do it. So the supernova classification is a spectroscopic classification. It basically divides the supernova into 2 families. If there is hydrogen in the spectra, we call it type 2. If there is no hydrogen, we call type 1. Today, the taxonomy is much more rich. There is a big variety of classes and subclasses of supernovae. Nevertheless, we can still divide
this rich variety in two families. The type 1a that you see here, the so-called thermonuclear supernovae. There are supernovae that we use for cosmological studies to measure the cosmological parameters, for example, and all the others that are core collapse supernovae that obviously, as you see here, HAPA, right side, they come from progenitor that have at least 8 solar masses. And the supernovae associated with gamma ray burst are a tiny fraction of 1C supernovae. We call them also hypernovae or broadline 1C supernovae. All these definitions are equivalent. And this gives you an idea of what is the structure of the star, the progenitor star, at the moment, at the epoch in which the collapse of the core. You see here for type 2, we have the onion structure and the layer is hydrogen. For type 1b, there is not anymore the hydrogen layer, the external layer, so the last layer is a helium, and that's why we see in the spectrum helium lines and not anymore hydrogen lines. And finally, 1C, they are the one connected with the gamma ray burst. We don't see in the spectra hydrogen, we don't see helium, but because these layers have been lost during the secular evolution of the stellar evolution, secular evolution. So the observational properties of gamma ray burst are the spectra, obviously, that doesn't show, as I told you right now, hydrogen, helium. But the other important characteristic are these broad line structure. And this, if you compare with a standard, with the spectrum of a standard core collapse supernova, you see that the structure here in the standard right side panel, these lines are much more narrow. And that means that the broad feature that you see in gamma ray burst supernova, left side panel, they correspond to a larger expansion velocity of the order of 10% of speed of light. This is well represented by this plot in which you have a photospheric velocity here against the time after the supernova explosion. And these 30,000 kilometers per second, once you combine with the mass of the jet, that correspond to a kinetic energy of the order of 10 to the 52 erg, which is 10 times larger than standard core collapse supernovae. The range of luminosity is also pretty broad. We can have broadline supernovae as faint as the faintest standard core collapse supernovae, as is this case here, 94I. This is a standard 1B supernova with the 2010 BH, this is broadline, and they can be as bright as type 1A supernovae. That implies that the mass of nickel that is synthesized in the last stages of stellar evolution could vary by a lot, from probably 0 fraction of tenth of solar masses up to 0.5, 0.6, or even 0.7 solar masses. And also another important point is that the explosions are aspherical, and this can derive by studying the profiles of the oxygen and iron lines obtained during the nebular stages. And also this derive from an independent measurement. I don't have time to, but evidence is pretty solid. And if you, this is a nice paper that's been published now 15 years ago, where we found that at least 50% of 1b/c supernovae are produced in a spherical explosion. And from this lack of symmetry in the explosion has an important consequences when you make the modeling of the explosion of the progenitor, because obviously the quest for energy decrease dramatically when you give up to the idea that there is a spherical outburst. Basically, from 30 times 10 to the 51 erg, you can decrease, that was the energy associated with the 98 BW, assuming a 4 pi emission. Well, that correspond to 30 times the energy, kinetic energy associated with 87A. Yes, you can decrease this by up to 70%. So what are these progenitors? Well, there are two ways to approach this problem. One is a direct way that can be carried out only by studying the nearby objects. And why only the nearby objects will appear clear in a moment. Basically, you collect the largest amount of spectra during different epochs, and you compare the observed spectra, the observed sequence of spectra, with the synthetic spectra that have been elaborated by theoreticians. And then you do the same by comparing the observed light curves with the synthetic light curves. And when the match is satisfactory, you can get out, you can not get out, you have the result. And so, as you see, we can estimate that the mass of this progenitor's gamma ray burst are between 20-25 solar masses up to 45-50 solar masses. But then you have another approach that is based on the study of gamma ray burst and host of gamma ray burst in cosmological distances. And the observation of the empirical basis for this approach is provided by this paper by Andy Fruiter. He studied the host of core collapse supernova. You see at left, the panel at left, and you can compare with the host of gamma ray burst, a long duration gamma ray burst, obviously. And immediately you see also from a simple glance that the morphology of the host are pretty different. Here we have well-designed spirals for core collapse, standard core collapse supernovae, while the host of long duration gamma ray burst show irregular shapes, a disturbed morphology. But let's say, let me say the critical, the key plot is the following. Look at here we have in Y the fraction of supernovae or long duration gamma ray burst. In x-axis we have the fraction of light of the host galaxy. Look, for example, to the blue solid line, type 2 supernovae. You see here the 50% of type 2 supernovae track the 50% of the light of the host. Go, for example, and look at the solid red line, Taiwanese. Again, the 50% of Taiwanese supernovae track almost the 50% of the light of the host. But when you go to and look at long duration gamma ray burst, the black solid line, you see that 50% of long duration gamma ray bursts track almost 90% of the light of the host. And the same trend is exhibited by Taiwan C supernova, the solid green line. What does it mean this? That Taiwan C supernova and long duration gamma ray bursts erupt in the brightest regions of their host. In other words, gamma ray bursts are so massive and they live so short that the progenitors don't have time to drift apart from the location where they were born. In other words, they born and die in the same place. And when you assume typical size for the H2V, for the star formation region, and typical velocity for these stars inside the cloud, this is a paper that we have done with Cody Raskin some years ago. You see that the gamma ray burst progenitors stay into the tracks of between 30 and 15 solar masses, which is in great agreement with the direct measurement of the masses that have been carried out by studying the local gamma ray burst. What is the size of gamma ray burst? Well, the size of gamma ray burst, the possibility to answer to this question comes from from gamma ray burst 060218 associated with supernova 2006 AJ. I want to take your attention on this plot. Well, not on this, but on the next one. This is a black body component that has been detected in the SWIFT data. And this black body component is decreasing in temperature as soon as it is increasing in size. And when you compare the x-axis, that is time, with the size radius, we derive a velocity of 30,000 kilometers per second, which incidentally is exactly what has been observed for the expansion velocity of 98 BW, for example. So the typical expansion velocity of the jet of hypernova or broadline supernovae. And when you go back and you extrapolate back to this data, to this data point here, you have and you can estimate the size of the progenitors, 4 times 10 to the 11 centimeters. And now in this cartoon, I've summarized all the data that we know for the progenitors of core collapse supernovae. So we have for a standard type 2 supernova that comes from a red supergiant, a radius of 4 times 10 to the 13 centimeters. For the progenitor of type of 87A, that was a blue supergiant, is 4 times 10 to the 12 centimeters. And for the radius of 2006 AJ, so 4 times 10 to the 11 centimeters, that is the size of a Wolf-Rayet star. So the progenitor of long duration gamma ray bursts are Wolf-Rayet star. What is the rate of long duration gamma ray bursts? There are a number of estimated, and all of them converge towards 0.7 gamma ray burst per kiloparsec cube per year. Then you have to compare this rate with the rate of 1 BC that normally is based on the 2 historical classical supernova survey, the Asiago survey and the Leak survey. And so that now you compare this GRB rate with the rate of 1 BC supernova per gigaparsec cube per year, after correction for beaming. That means that is something that it is not clear, but I mean this large interval is not due is not representative. It doesn't represent an uncertainty in the measurement. Well, also that but probably represent a real physical range of beaming factor, of opening angle. And when you do that, you find that gamma ray burst over Taiwan BC supernova range between 1.5% up to a number as small as 0.02%. So conclusions, GRBs are very rare phenomena. This ratio I'm seeing in the most favorable case is 1.5%. The rate between 1 BC and standard core collapse supernova is 30%. So this ratio, gamma ray burst over core collapse, is 0.005. And when you compare this with a simple, with the data, with the ratio that comes from a simple salpeter IMF, you find a ratio that is much larger than that. So this produces an incredible question that still has not received an exhaustive answer. What causes some small fraction of core collapse supernovae to produce observable gamma ray burst, while the majority do not? Sorry, Mr. Chairman, how much time I have?
Oh, I didn't count the time, but you can continue, I think. But you need to leave some time for the lunch because the next session will start at 3 p.m.
So I have 5 minutes.
Okay, okay.
So what is apparent?
Sì, evolvi su questo punto. C'è tempo.
Sì, okay, I'm coming. Okay. So we need
evolvi su questo punto.
Yes, I'm trying. I'm going to expand this point. So there are special conditions are requested to progenitor star, massive progenitor star, sorry, to stars to be GRV progenitor. First one we have seen is pretty obvious. They have to be massive. This comes directly from observations. Then they have lost the hydrogen and helium envelopes. And this comes also from observations. We have seen in the spectra, there is not any more hydrogen, there is not any more helium in this spectra, and we have measured the size, and then it turns that they are Wolf-Rayet star. From observation also, we have derived that these explosions are asymmetric. Then there is another important point, and that comes from the study of the host galaxies, that these objects tend to explode in low metallicity star-forming environment. Look, for example, at this plot. Okay, these are the luminosities versus luminosity versus metallicity plot for 53,000 galaxies from the Sloan Digital Sky Survey. Open diamonds are the median of each beam. The dark and light dark region represent the 1 sigma and 2 sigma region. The red symbol, the star and the circles are the long duration, subluminous long duration gamma ray burst. The blue ones are cosmological long duration gamma ray burst. And the black symbols, square and triangle, are broadline 1 BC supernovae. And you see that the object for which were possible to determine the two parameters, well, they tend to populate the low metallicity region. The other special condition that I was considering is a binarity. And these come from a number also of historical papers. There is, for example, now I don't see anymore the reference, but however, in papers, in the papers that you see here below in my slides, in several of them, there is included the statement that at least 70% of massive stars are in binary system. And this brings to a model that has been developed in these last 10 years and maybe 15 years in Pescara by Raymond Ruffini and his group that we call binary hypernova scenario. Sometimes a binary driven hypernova scenario. And here you have the reference paper that started to this idea to try to explain a gamma ray burst through a real model that take into account the fact that very likely most of these progenitor, if not all of them, are in massive binary system. And I suggest for people who want to go deeper, because I can't do that right now, to look at this nice paper. Is a brief review of binary driven hypernova model that has been published recently by Jorge Rueda, Ruffini, and Moradi, and Wang. The last condition that I was considering is high rotation. High rotation is fundamental because, okay, basically, if you look at this slide, the upper branch is the so-called, let's call normal evolution. So slow rotation, you have, finally you end with a red supergiant with a huge envelope of hydrogen. In the model characterized by high rotation, rapid rotation, the star rotates fast enough to avoid the red supergiant phase, and it becomes directly a Wolf-Rayet. This is important because if this star doesn't lose the envelope, it means that it retains a high fraction of the angular momentum. That is, let's say, the engine that will feed the jet inside when the gamma ray burst will be formed. Conclusions. Okay, observation of core collapse supernovae reveal the existence of a continuum of properties among the different supernova classes. So in other words, yes, we can claim, I will show to you a nice slide at the beginning with a huge variety of supernova classes. However, there is, as I summarize here, a continuum of property in between these different classes. And here I've reported the main data, but I don't have time to comment them. And then there is something that is not clear yet. What produced the observed variety in long duration gamma ray burst phenomenology? We have an incredible, in spite of this family of objects is a simple tiny fraction of 1C supernovae. Well, they show exhibited this huge variety in phenomena in terms of gamma budget associated with the bright Taiwan BC supernovae, faint Wang BC, and so on. And now let me finally talk a little bit, just 1 minute, about the reason for which we are talking about science today, that is the birthday of Raymond. So I was asking myself when I was preparing this talk, when I met Raymond first time, when I met him first time, I was a student in Padua and I was in the audience, so we didn't have a chance to interact. But then I'm sure that this, I showed this paper, but that has nothing to do with my topic today, because I was a space telescope. I share my office with Malcolm Longueur, and at a certain point, I've seen Raymond Ruffini come into this office and talk with Malcolm, and then he was looking to my table. I was preparing a journal club on microlensing on this paper, and he started to ask me and pose a number of questions, and then I remember that he started to give to me hints, precious hints to improve my presentation. And that is something that I never forgot, because of obviously I knew him, but he didn't know me. Nevertheless, he tried to help me immediately. Then we were, obviously we start, I mean, we have known each other for 27 years now. So I invited him to come to Naples, giving this public talk on the black hole, and just to show the audience was completely packed to say how popular he is Remo Ruffini in Italy. And so auguri Remo e grazie di tutto.
Grazie a te. Però vorrei dirti qualche cosa.
Wait, no, sorry. Just I know that there will be a school in July in Nice, and I promise that we can discuss into the details each of these points, because
yes.
Each of these points deserve probably a 20-30 minutes discussion, each of these points at least. And so we can go into the details, but obviously in 20 minutes I couldn't do that, okay?
But let me tell you the new things.
Okay.
The new things we taught before, they were 3 BdHN, okay?
Yeah.
BdHN 1 around 10 to the 50, 49, 50. Then BdHN 2 between 10 to the 50 and 10 to the 52. BdHN 3 over 10 to the 52 to 10 to the 55. What we understand now since a few days is that BdHN 1, they do not exist. They are just supernova, single, not binary.
Okay.
BdH2, they exist, and BdHN3, of course, also. But the key point is that now the responsible of the energy, both of BdHN2 and BdHN3, is the collapse of the CO core. The collapse of the CO core generates many things. Among them, one among them is the supernova. One among them. But the BdHN2 and BdHN3 are just the CO collapse. And the most important to understand is that the CO core collapse can be up to 10 to the 55. In other words, the father, the mother of the GRB are many different processes. And the total energy can be up to 10 to the 54, 10 to the 55. But this energy is just the energy of the CO core. No emphasis on the supernova, all the emphasis in the CO core. I have to stop now because I have to do something and I will be at the villa later.
Okay.
Grazie di tutto.
Okay, thank you, Professor Della Valle. Any comments on the question? Okay, if we know, let's go to the next speaker, the last speaker in the morning or in the noon. So the professor Ansardi and his student Hernandez. Hello, can you hear me? Yeah, hello, we can hear you. I will speak for the first couple of minutes, and then I will take over Benjamin Hernandez, who will discuss something about the extension of magnetohydrodynamics beyond the ideal case. And first of all, I would like to thank you, the organizers of this conference, for the possibility to speak in this occasion of Professor Ruffini's 80th birthday. And I would like just a couple of minutes first to wish to give him my best wishes for his 80th birthday. Now, I think it's not up to me to now comment about the many great scientific results connected with general relativity that in the past decades Professor Ruffini and his group achieved, because I think this has been quite well discussed and is witnessed also by the exceptional quality and level of speakers in this conference. However, I would like to remember a little bit how I came in contact with Professor Ruffini and with the ICRA and later with ICRANet at the time when I was a student and when basically general relativity was considered sometimes still an accessory subject in physics, in the sense that I remember when I was much younger that still you really needed to be a GR aficionado to really spend the time in considering general relativistic corrections to many physical processes, to the point that very often people were disregarding the importance that such corrections actually have for real physical systems. At that time, in fact, it was often claimed that it was much more important to start by neglecting completely the general relativistic effects in the systems that we were studying, and then consider them at a later time. I was never completely convinced by this, because actually it turns out that while this seems a very logical and potentially wise approach, it turns actually in practice out that when you add general relativistic effects, very often you have some complete shift in the paradigm and in the treatment that you are considering, so that many concepts and many tools that you can develop when you do not factor in general relativistic effects become almost useless when we study general relativistic systems. So the generalization is not straightforward, and most of the time it forces you to abandon some ideas. And I think in many of the talks that we have seen in these days, we have exactly witnessed this fact that is, I think, very clear in some of the models that have also been discussed in this morning and today. And another comment that I would like to make about my first encounter with Professor Ruffini, ICRA and ICRANet, dates back to some decades ago when I was visiting Professor Werner Israel in Canada, and we were discussing about the importance of general relativity and to take into account general relativistic corrections to understand in detail the behavior of astrophysical systems. At the time, I think many Newtonian models were preferred on average in the literature. And he told me that it would have been a very good idea to discuss some of the topics with Professor Ruffini, and he mentioned very explicitly not only about his great scientific and physics input that I could have received, but also the fact that he has always been very supportive with young people. And I think this is something I wanted to mention today, because we are working on problems where more and more we know that we probably will not be able to see them to the end, because the simple things have been solved, and the more complex ones require a lot of time. And it's very important that we pass our understanding and our knowledge to future generations. And I think with ICRA and with ICRANet, this is something that I certainly think Professor Ruffini has done over the past decades, which is as important, I think, as the physics results that have been achieved in these fruitful collaborations. And so this is where I would like to conclude my wishes for his 80th birthday, and my thanks for all the activity that has revolved around his group over the years, and in some way to witness my appreciation for his always strong support of young physicists and for new generations in physics. I would like now to pass the proceedings to Benjamin Hernandez. He's a master student. He's in Trieste. He graduated just a couple of months ago, and he did some preliminary work on studying magnetohydrodynamics beyond what is usually considered as the ideal case, which is the most common one, the most common use in astrophysical applications. So thank you again for the invitation, and I pass now the proceedings to Benjamin. Thank you very much.
Can you hear me?
Yes, we can hear.
Okay, perfect. So good morning, good lunch break. First and foremost, I would like to thank Professor Ansoli for this opportunity and all the organizers and researchers here. I am Benjamin Hernandez, and I would like to briefly give a small presentation on some key concepts in magnetodynamics. I will share my screen. Perfect. Okay, so I will talk about magnetodynamics and specifically on some hopefully interesting ideas behind the extension beyond the ideal limit. So as we all know, magnetodynamics is one of the many frameworks we have to study plasmas. We just the talk before the lunch break, we discussed kinetic theory, and magnetodynamics is another framework. It is the macroscopic framework. It is based on the fluid model, and therefore time and spatial scales have to be big compared to the characteristic scales of the microscopic theory. Usually, we are working with one component fluid, as it is in the ideal and in the standard model. But as we shall see, there has been some interest in multi-component fluids, mainly in two fluid model. The ideal approximation is the main framework in which all the numerical work is done at the moment. And in the ideal approximation, we basically consider the fluid, the plasma, as a perfect conductor. If we take a look on the Ohm's law on the right, in the ideal limit, we take the resistivity to 0, but we want to keep a finite for current. This means that with this version of Ohm's law, which is the simpler version of Ohm's law, the electric field with respect to the fluid must be 0. This has some pretty big implications, since given the fact that the electric field is 0, we are reducing a number of independent variables in our system, because the evolution of the electric field is completely determined by the evolution of the magnetic field and of the velocity field of the plasma. This means that this approximation, it is easier from a mathematical and a computational standpoint, because in numerical simulations, usually the source term, the term which encompasses the forecurrent, is the difficult one to treat. This is because we don't need to have to work with both Maxwell's equations. We can just work with the homogeneous one. And since we have reduced our number of variables. Of course, this is not only a trick, a mathematical trick, but it has been verified countless of times through experimental and experimental verification and observations. We can just think very recently in 2019 about the work on M87 and by the Event Horizon team. However, as with most approximations, it has some limitations and some concepts. First and foremost, it is impossible to describe and model magnetic reconnection phenomena in an ideal framework. And this is quite important because at the moment, magnetic reconnection is a very hot topic in astrophysics, because we think it is at the core of many important processes, from solar flares to particle jets in accretion disks of black holes. Moreover, it has been argued recently that the applicability of ideal matter dynamics is somewhat restricted to the inner regions of the accretion disk, and that the resistivity is of fundamental importance to accurately describe the formation and evolution of our physical system, of our accretion disk. So I will briefly present two alternative models to the standard magnetohydrodynamic model, and in particular to the ideal framework. We will see in the first part a brief introduction to the theory of polarizable fluids, while in the second part I will spend a few words on the two fluid models. Polarizable fluids have been perhaps unfairly neglected until very recently in general relativity, and particularly in the field of covariant magnetohydrodynamics. In my thesis work, we adopted some results by Dixon, who in this book I listed here, under the assumption of thermodynamic equilibrium for our system of charged fluid, was able to obtain a general expression for the energy momentum tensor of this system, which is not simply the sum of the perfect fluid and the free electromagnetic field, as it is usually done in standard matter dynamics, but this generalized tensor contains extra terms. These extra terms, you can see on the right, are listed as the T2 and T3, are mixed terms. This means that they cannot be attributed exclusively to the plasma or to the electromagnetic field, and are characteristic of a polarizable medium. In particular, in my model and in our model, we consider only the term T3 as and we neglected the second term. Dixon's model can be used, and it has been used to justify the ideal framework, and therefore can be used to generalize it. Dixon obtained his energy momentum tensor by supposing a fluid at thermodynamic equilibrium and by supposing linear constitutive relations for our medium, for our plasma. If one takes Dixon's model and makes the assumption of that an ideal Ohm's law holds, and one assumes constant susceptibility, constant electric and constant magnetic susceptibility, one obtains directly ideal magnetohydrodynamics. This means if we can relax some of these hypotheses, we can generalize the ideal model. In particular, we derived a full set of generativistic magnetodynamic equations, relaxing the ideal Ohm's law condition. Of course, since by relaxing the ideal condition, we are working with resistive equations, these are, of course, more mathematically complex than the ideal generativistic magnetodynamic equations. However, we found that this complexity, which is unfortunately also a computational complexity, can be mainly attributed to the presence of the current terms. And this is characteristic of any resistive model, not of this model, which is based on a theory of polarizable fluid. This means that this model on polarizable fluids, polarizable relativistic fluids, can be an interesting and somewhat valid alternative to an ideal and resistive magnetodynamics, in general to the standard magnetodynamic model, and therefore to the ideal magnetodynamic model used nowadays. I would like to finish my talk with just by spending a few words on some two fluid models, which are very interesting and are somewhat of a niche in the world of magnetodynamics. In the two fluid models, we basically treat the positive and negative stream of particles independently. This field was started or made popular by Ramon Khanna's Lemma work, where he was able to obtain a generalized version of Ohm's law. In particular, he obtained it in the cold plasma limit, and he restricted himself in the Kerr metric. What is really interesting about Khanna's work is the fact that non-generalized versions of Ohm's law, like the one you can find at the center, suffer from a series of problems. This is mainly because they ignore some important effects which derive from the interaction between charged particles and our charge carriers. And the fact that we are able to obtain a generalized version of Ohm's law, and here I must stress that in the standard model and the ideal model, the Ohm's law is not derived, but is imposed. The fact that we are able to derive a generalized version is really interesting. It can give us some great tools. In particular, in my thesis work, I worked on the two-fluid model by Shinji Koide. It's a very recent model. It was published around 2009, sorry. And starting from the conservation laws for our two-fluid system, he was able to obtain a generalized version of Ohm's law, which generalizes the seminal work of Khan. Here we can see the generalized version of Ohm's law. On the left-hand side, we can see some inertia terms which depend on the mass of our carriers. And on the right-hand side, we can see that we have the Hall terms and pressure gradient terms, and also the classical resistivity term. The friction term can be written in terms of a resistivity coefficient. What is really interesting about this version of Ohm's law is the fact that it is possible to have magnetic connection, and so to simulate magnetic connection, even in the non-resistive limit. This has been shown in a few papers by Commisso and Asenko. And this is really, really important because we saw before that in the ideal limit, where the resistivity is 0, it is not possible to simulate and it's not possible to have magnetic connection. However, in this case, by retaining all of these new terms, like the inertial terms, Hall terms, it is possible to have magnetic connection. We have still some connection equations, so some quantities that are connected, but they are not directly are not the magnetic field, but they are some generalized tensors, which are called magnetofluid tensors. I would like to thank for your attention.
Okay, so any question or comments? Okay, so thank you for having.
Thank you.
So, thank you. So now is the lunchtime. So let's finish the session.
Excuse me, can I take a word? Someone? Still, Abhishek Medu. It's me. Professor Ruffini, are you here?
I think he is temporarily disconnected for the moment.
Oh. Okay.
Okay, so let's resume the meeting at 3 p.m. Okay, have a nice lunch and enjoy the sun of this